Hello and welcome to Space Historians, where curiosity settles in softly and the universe unfolds at the pace of your breathing. Tonight, we're not looking at the bright things, the galaxies that shine across the darkness, or the stars that catch your eye when you glance upward. We're turning our attention to something quieter, something that rarely gets noticed in the grand stories we tell about space. We're looking at what lies between the galaxies, the vast, seemingly empty stretches that separate one island of light from another, the dark oceans of space where almost nothing seems to exist. Before we begin drifting through these quiet regions, I wonder where you are right now. Maybe you're tucked under blankets with just enough light to see by, or perhaps you're in complete darkness, letting the day finally fall away. Maybe the world outside your window has gone still, and all that remains is the soft rhythm of your own thoughts. We're about to explore, surrounded by the same space that stretches between the galaxies, even if you can't see it. If this kind of wandering helps you unwind, if cosmic questions wrapped in calm bring you peace before sleep, I'd be grateful if you gave this a like or subscribed. It helps this quiet corner of science reach others who might need a gentle place to rest their minds. And for those already here, thank you. You're part of this voyage into the vastness. So take a breath now. Let it out slowly. Let your shoulders drop, your jaw relax, your thoughts begin to drift. Tonight, we're going somewhere that seems like nothing but turns out to be everything. We're exploring the spaces that connect all the bright things, the invisible ocean that holds the universe together. When you picture space, you might imagine it as empty, a perfect vacuum, a void, an absence of everything. And compared to Earth, with its dense atmosphere and solid ground, space does seem empty, but the universe has a way of hiding things in plain sight. What looks like nothing from one angle turns out to be something profound from another. The spaces between galaxies are enormous. The nearest large galaxy to our own Milky Way, Andromeda, sits about 2.5 million light-years away. That's the distance light travels in 2.5 million years, and that's just our closest neighbour. Most galaxies are much farther apart. Between them lies what astronomers call the intergalactic medium, a realm so vast and so thin that it defies ordinary description. But thin doesn't mean absent. Even in the emptiest regions, even in the darkest voids between galaxy clusters, there's still something there. Atoms scattered so thinly, you might find only 1 or 2 in every cubic meter. Photons from the cosmic microwave background, the afterglow of the Big Bang passing through silently. Gravitational waves rippling across space-time itself. Dark matter weaving invisible filaments through the darkness. And dark energy, the mysterious force that pushes everything apart, filling every corner of space. What lies between galaxies, then, isn't nothing. It's a different kind of something. A quiet presence that shapes the universe more than the bright galaxies ever could. It's the scaffolding that holds everything in place, the canvas on which creation paints itself, the breath between words in the universe's long story. Tonight, we'll drift through these spaces together, slowly and gently. We'll discover what fills the darkness, what connects the islands of light, what makes the universe more than just a collection of scattered stars. You don't need to understand every detail or remember every fact. Just let the ideas wash over you like waves on a shore, each one leaving a small impression before receding into the next. The universe is patient. It's been expanding and evolving for nearly 14 billion years. It can wait for you to catch up. And as you lie there, breathing slowly, letting your mind wander through the cosmic dark, you might find that the space between galaxies isn't so different from the space inside your own thoughts. Both are vast, Both seem empty at first glance, but both, when you look closer, are filled with quiet motion, with invisible forces, with connections you never noticed before. So settle in. Let the day dissolve. Let the universe open up around you, not rushing or demanding, but simply inviting you to wonder. The spaces between galaxies are waiting, and they have stories to tell, if you're willing to listen softly enough to hear them. For most of human history, we didn't know there were galaxies at all. The Milky Way, our home, seemed to be the entire universe. Those faint smudges of light scattered across the night sky, the nebulae that astronomers catalogued with quiet patience, were thought to be clouds of gas within our own cosmic neighbourhood. The idea that they might be distant cities of stars, separate from our own, seemed almost too vast to consider. Then, in the early 20th century, everything changed. Edwin Hubble, using the most powerful telescope available at the time, measured the distance to one of those fuzzy patches, the Andromeda Nebula. What he found was staggering. Andromeda wasn't a cloud of gas nearby. It was an entire galaxy, a collection of hundreds of billions of stars, sitting more than 2 million light-years away. In that moment, the universe grew impossibly larger. But Hubble's discovery did more than just expand our cosmic address. It revealed something equally profound. If Andromeda was a separate galaxy, then the space between it and the Milky Way must be vast beyond comprehension. And if two galaxies could be separated by such enormous distances, then space itself, the fabric of the universe, must extend much farther than anyone had imagined. That realization was the hook, the moment when humanity first understood that the universe wasn't a crowded collection of stars but a vast expanse punctuated by islands of light. The spaces between those islands weren't just gaps, they were regions in their own right, places that demanded exploration even though they seemed to contain nothing at all. At first, astronomers assumed those spaces truly were empty. After all, if they contained matter or energy in any meaningful amount, wouldn't we see it? Wouldn't it shine, or block light, or leave some trace of its existence? But the more carefully scientists looked, the more they realized that absence of visibility didn't mean absence of presence. The intergalactic medium, as it came to be called, was simply too diffuse, too cold, too faint to see directly. The hook wasn't just about discovering that galaxies existed. It was about discovering that between them lay something mysterious, something that would take decades of patient observation and theoretical work to understand. What seemed like the simplest question, what's out there in the dark between the bright things, turned out to have the most complex and beautiful answer. Think about what that moment meant. For the first time, humanity realized that most of the universe's volume wasn't filled with stars or planets, or anything we could see. It was filled with something else entirely, something that didn't announce itself with light or heat or sound, something that simply existed, quietly holding the visible universe in place. That's a strange thought, isn't it? The idea that most of reality is invisible, that the bright things we focus on are just tiny islands in a vast ocean we can't see. It's humbling in a way, but also oddly comforting, because if the universe can hide so much in plain sight, then maybe there's more to everything than we first assume. Maybe what seems empty is actually full. Maybe what seems absent is actually present, just in ways we haven't learned to perceive yet. The moment of realization came gradually, not all at once. First, there was Hubble's measurement, showing that galaxies were separate structures. Then came observations of how those galaxies moved, revealing that space itself was expanding, carrying the galaxies apart like dots on an inflating balloon. Then came more detailed studies, showing that between the galaxies there had to be something some medium through which light travelled, some substance that filled the void. Each discovery added another layer to the picture. The spaces between galaxies weren't just empty stretches of nothing. They were active regions filled with matter and energy we couldn't see directly but whose presence we could infer from its effects. Gas atoms scattered thinly through space, radiation left over from the Big Bang, mysterious dark matter providing gravitational scaffolding, and most recently, dark energy, the force driving the universe's accelerating expansion. But perhaps the most important part of that initial realization was something subtler. It was the understanding that the universe is more connected than it appears. The galaxies might seem isolated, separated by vast gulfs of darkness, but they're all part of the same continuous fabric. The space between them isn't a barrier, it's a bridge. It's what allows galaxies to influence each other across enormous distances, what carries light from one to another, what makes the universe a single, unified whole rather than a collection of disconnected pieces. When you think about it that way, the spaces between galaxies become just as important as the galaxies themselves, maybe more important, because without those spaces, without that connecting medium, the universe would be fundamentally different. Galaxies wouldn't form the way they do, light wouldn't travel the way it does. The cosmic web, that grand pattern of filaments and voids that defines the universe's large-scale structure, wouldn't exist. The hook, then, wasn't just about finding that space between galaxies exists. It was about realizing that what lies there matters, that the darkness is active, that the emptiness is full, that the void is alive with processes we're only beginning to understand. And that to truly know the universe, we have to explore not just the bright islands but the quiet oceans between them. As you lie there, letting this thought settle, you might notice something. The space around you, the air in your room, seems empty too at first glance, but it's filled with molecules, with light, with sound waves, with electromagnetic radiation from 1,000 sources. Your body moves through all of that without noticing it most of the time. The same is true of the space between galaxies. It seems empty, but it's filled with invisible presences that shape everything. In that sense, the moment we realized what lies between galaxies was also a moment of recognizing a larger truth. That reality contains layers we can't see directly. That absence is often just another form of presence. That the quiet spaces matter as much as the loud ones. And that sometimes the most important discoveries come not from looking at what shines, but from wondering about what doesn't. The hook caught humanity's imagination because it revealed a mystery hiding in the most obvious place, right there in the darkness we'd been staring at for thousands of years. We just hadn't thought to ask the right question until we understood how vast the universe truly was. Now, having asked that question, we're still discovering the answer, and every new layer we uncover makes the spaces between galaxies seem more wondrous, more essential, more alive. So as we begin this journey together, drifting through those spaces in thought, if not in body, remember that we're exploring something fundamental. Not the edges of the universe, but its heart. Not the exceptional places where things shine brightest, but the ordinary places where most of the universe simply is. The spaces between galaxies are the rule, not the exception. They're where the universe spends most of its volume, most of its time, most of its quiet existence. And that hook, that moment of realization that these spaces exist and matter, opens up everything that follows. It's the beginning of understanding not just what the universe contains, but how it works, how everything connects, how nothing is truly separate, how even the darkest, emptiest seeming places are part of the same continuous whole that includes you, me, Earth, the Milky Way, and everything else that exists. Let that thought rest gently in your mind as we move forward. The spaces between galaxies are waiting, patient and vast, and they're ready to share their secrets with anyone willing to drift through the darkness and listen to what the silence has to say. When we look at images of the universe, whether from powerful telescopes or artists' renderings, we see galaxies scattered across darkness like jewels on black velvet. They appear as isolated islands, each one a brilliant collection of stars floating in the void. But that image, beautiful as it is, doesn't capture the full truth, because between those islands lies something we can't easily photograph, something that exists in a state so diffuse it becomes nearly invisible. The setting for our exploration is unlike any place you've ever been. It's not a location in the usual sense. It's everywhere that isn't a galaxy. It's the majority of space itself. If you could somehow compress all the galaxies in the observable universe into a single point, the remaining emptiness would still stretch for billions upon billions of light years in every direction. That's the canvas we're examining. That's the stage on which the cosmic drama unfolds. To understand this setting, we need to first grasp just how empty space can be. On Earth, even our best laboratory vacuums contain trillions of atoms per cubic centimetre. The air around you right now has about 10 to the 19th molecules per cubic centimetre, an incomprehensibly large number. But in the intergalactic medium, in the spaces between galaxies, you might find only 1 atom per cubic metre, sometimes even less. That's a degree of emptiness that's hard to visualize. Imagine a cube of space, 1 meter on each side. Fill it with all the matter in that region of intergalactic space, and you'd have, on average, a single hydrogen atom. Maybe 2 if you're in a slightly denser region. Everything else is just a space. Pure geometric extension with almost nothing in it. And yet, even in that near-perfect vacuum, things are happening. That single atom is there for a reason. It's part of a larger structure, a faint web of matter that connects all the galaxies. It might be drifting slowly toward a nearby galaxy, pulled by gravity over billions of years. Or it might be part of a thin filament of gas stretching between galaxy clusters, so rarefied it's essentially invisible but still gravitationally significant. The temperature of this setting varies dramatically depending on where you are. In the deepest voids, the spaces between galaxy clusters where matter is thinnest, the temperature might be just a few degrees above absolute zero. The faint atoms there move slowly, barely interacting, cooled by billions of years of cosmic expansion. But near galaxies and along the filaments that connect them, the gas can be hot, sometimes millions of degrees. That sounds contradictory, doesn't it? How can something so empty be so hot? The answer lies in energy. When gas falls into gravitational wells, when it's heated by radiation from nearby stars and galaxies, when shock waves from ancient collisions pass through it, the atoms gain energy. They move faster. In thermodynamic terms, they become hot. But because there are so few of them, they carry very little total heat. An astronaut floating in million-degree gas between galaxies wouldn't burn. There simply aren't enough particles to transfer that energy. This is the setting we're exploring. A place where density and temperature can vary by orders of magnitude, where the rules of physics operate in extreme conditions we can barely replicate on Earth, where time moves with a patience that makes geological timescales seem rushed. It's a place defined more by what it doesn't have than what it does. No air, no sound, no solid ground, no reference points except the distant galaxies themselves. If you could somehow stand in one of these intergalactic spaces, truly float there without a spacecraft or suit, just existing in thought as a point of awareness, what would you perceive? Darkness, certainly. Not the darkness of a closed room or a moonless night, but an absolute darkness broken only by the faint smudges of distant galaxies. Those galaxies would be so far away that even the nearest might appear no brighter than a dim star appears from Earth. You'd be surrounded by silence, not the quiet of a soundproof room, but the complete absence of any medium for sound to travel through. There would be no wind because there's no air. No temperature you could feel because there's nothing to touch your skin. You'd be isolated in a way that's impossible to experience anywhere on Earth, separated from everything by distances so vast that light itself takes millions of years to cross them. And yet, you wouldn't be entirely alone. Every second, neutrinos from distant stars and galaxies would pass through you by the trillions, moving at nearly the speed of light, completely indifferent to your presence. Cosmic rays, high-energy particles accelerated by supernova and black holes, would occasionally streak past. Photons from the cosmic microwave background, the oldest light in the universe, would bathe you in faint, invisible radiation. The setting is also in constant motion, though that motion is imperceptible on human timescales. Space itself is expanding, carrying galaxies farther apart with each passing moment. The atoms that make up the intergalactic medium are drifting, following gravitational currents that flow through the cosmic web. Everything is moving, evolving, changing, just so slowly that it seems static. This is where most of the universe exists, not in the bright cores of galaxies or the dense atmospheres of planets, but out here in the quiet expanse between things. This is the baseline, the default state of cosmic existence. The galaxies are the exceptions, brief local concentrations of matter in an ocean of near emptiness. We tend to focus on those exceptions because they're bright and interesting, but the setting itself, the vast intergalactic medium, is what gives the universe its character. When cosmologists model the universe's evolution, they don't just track what happens inside galaxies, they track what happens in the spaces between them. They simulate how gas flows along dark matter filaments, how it heats and cools, how it occasionally falls into galaxies to fuel new generations of stars. The intergalactic medium isn't just background, it's an active participant in cosmic evolution, a reservoir of matter that galaxies draw from and return to. The setting also has history written into it. When astronomers observe the intergalactic medium, looking at how it absorbs light from distant quasars, they can read that history. The patterns of absorption tell them about the density and temperature of the gas at different times in the universe's past. They reveal how the first stars and galaxies heated their surroundings, how supernova explosions enriched the medium with heavy elements, how the cosmic web formed and evolved. In a sense, the intergalactic medium is a record keeper. It remembers what the universe has been through, storing that information in the distribution and composition of its sparse atoms. Every element heavier than helium, every carbon atom or oxygen atom drifting through intergalactic space, came from a star. It's a reminder that even the emptiest places carry traces of the universe's active past. The setting is also remarkably uniform on the larger scales. Look at the intergalactic medium in one direction, and it has roughly the same properties as in any other direction. The same density, the same temperature distribution, the same composition. This uniformity is one of the most important features of the universe. It tells us that the cosmos is, fundamentally, the same everywhere. There's no special center, no preferred direction, no cosmic axis around which everything revolves. But zoom in a bit, and you find structure. The cosmic web, that grand pattern of filaments and voids, emerges from the uniformity like a hidden design. The intergalactic medium isn't spread evenly through space. It's concentrated along filaments, thin threads of matter that connect galaxy clusters like a three-dimensional spider web. Between those filaments are enormous voids, regions where the density drops even lower than average. This structure formed over billions of years through gravity's patient work. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. But those tiny variations were enough. Regions that were slightly denser pulled in more matter, becoming denser still. Regions that were slightly less dense lost matter to their surroundings, becoming emptier. Over time, this process amplified the initial variations until they became the cosmic web we see today. The setting, then, is both simple and complex. Simple in its basic composition, mostly hydrogen with a bit of helium and traces of heavier elements, but complex in its structure, its temperature variations, its relationship with the galaxies, and dark matter that shape it. It's a place where almost nothing exists, yet where that almost nothing plays a crucial role in determining how the universe works. As you imagine this setting, this vast intergalactic canvas, let yourself feel the scale of it. The distances are so enormous that light, moving at 300,000 kilometers per second, takes millions or billions of years to cross them. The densities are so low that calling them a vacuum doesn't quite capture it. And yet, this is the universe's natural state. This is what most of space is like. There's something peaceful about that, isn't there? The idea that most of the universe is quiet, still, nearly empty, that between all the dramatic events, the exploding stars and colliding galaxies, there are these enormous stretches of calm. The intergalactic medium doesn't demand attention. It doesn't shine or pulse or roar. It simply exists, holding everything together in its gentle gravitational embrace. This is the setting we're exploring, the stage on which everything else plays out. And as we move deeper into understanding what lies between galaxies, we'll see that this seemingly empty canvas is actually filled with invisible threads, faint presences, and subtle forces that shape everything we can see. The darkness isn't absence, it's a different kind of presence, one that's learning to recognize and appreciate. The story of discovering what lies between galaxies is really a story about learning to see the invisible. For decades after astronomers realized that galaxies were separate structures, they assumed the spaces between them were truly empty. After all, they couldn't see anything there. No stars, no gas clouds, no visible matter of any kind. The darkness seemed complete. But in science, absence of evidence isn't always evidence of absence. Just because we can't see something doesn't mean it isn't there. And gradually, through clever observations and patient detective work, astronomers began to realize that the intergalactic medium wasn't empty at all. It was filled with matter and energy, just in forms too faint for ordinary telescopes to detect. The first hints came from an unexpected direction. In the 1930s, astronomer Fritz Zwicky was studying how galaxies in the Coma cluster moved. He measured their velocities and calculated how much mass the cluster needed to hold itself together through gravity. When he added up all the visible matter, all the stars and gas he could see, the numbers didn't add up. The galaxies were moving far too fast. There had to be more mass there, something invisible providing extra gravitational pull. Zwicky called this missing mass, dunkel materia, dark matter. At the time, few people took the idea seriously. It seemed more likely that Zwicky's measurements were wrong, or that there was visible matter he'd missed somehow. But he was right. There was something there, something massive, something that didn't shine. And that dark matter wasn't just inside galaxies. It was everywhere, filling the spaces between them, forming an invisible scaffolding that held the universe together. The discovery of dark matter was the first major revelation about what lies between galaxies. But it wasn't the last. As observational techniques improved, astronomers found more and more evidence of invisible presences in the intergalactic medium. They discovered that when light from distant quasars passed through space on its way to Earth, it was absorbed at specific wavelengths. Those absorption patterns revealed clouds of hydrogen gas scattered between galaxies, too diffuse to see directly but numerous enough to leave their fingerprints on passing light. This technique, studying quasar absorption lines, opened a window into the intergalactic medium. Suddenly, astronomers could map where the gas was, how dense it was, what temperature it had, even what elements it contained. The picture that emerged was surprising. The spaces between galaxies weren't empty. They were filled with a vast web of gas, most of it hydrogen, some of it heated to millions of degrees by falling into gravitational wells or being blasted by radiation from nearby galaxies. The discovery process continued. In the late 1990s, astronomers made another startling find. They were measuring distances to distant supernovae, trying to determine how fast the universe's expansion was slowing down. Everyone expected expansion to be decelerating, slowed by the gravitational pull of all the matter in the universe. But the observations showed the opposite. The expansion was speeding up. This acceleration could only be explained if there was some kind of energy filling space itself, pushing everything apart. They called it dark energy. And like dark matter, it was invisible. But unlike dark matter, which clumps and clusters, dark energy appeared to be spread perfectly uniformly throughout space, a property of the vacuum itself. And according to the observations, this dark energy made up about 70% of the universe's total energy content. Think about what that means. The majority of what fills the spaces between galaxies isn't matter at all. It's this mysterious dark energy, this cosmic pressure that's driving everything apart. The intergalactic medium isn't just full of faint gas and invisible dark matter. It's permeated by a force that's actively shaping the universe's fate, determining whether it will expand forever or eventually collapse back on itself. Each discovery added another layer to the picture. The spaces between galaxies contained scattered atoms of normal matter. They contained dark matter, providing gravitational structure. They contained dark energy, driving accelerated expansion. They contained radiation, the cosmic microwave background left over from the Big Bang, along with light from stars and galaxies, neutrinos, cosmic rays, and gravitational waves. What had seemed like pure emptiness turned out to be remarkably full. Not full in the way Earth's atmosphere is full, densely packed with molecules, but full in the sense that multiple forms of matter and energy coexisted there, each playing its own role in the cosmic story. The darkness wasn't absence, it was a different kind of presence, one that required new ways of seeing to detect. The process of discovery is still ongoing. With each new observatory, each new wavelength of light that astronomers learn to detect, they find more structure in the intergalactic medium. They've discovered faint glows of light from orphaned stars, kicked out of their galaxies by gravitational interactions. They've found hot gas along the filaments of the cosmic web, heated by the slow accumulation of matter. They've detected the faint signature of gravitational waves passing through, ripples in space-time from distant colliding black holes. Every discovery reinforces the same lesson. What seems empty is usually just hard to see. The universe doesn't give up its secrets easily. It hides most of its content in forms that don't emit light, in densities too low to photograph, in phenomena that require decades of patient observation to detect. But piece by piece, Measurement by measurement, the picture becomes clearer. The discovery of what lies between galaxies also changed how we understand the universe itself. It revealed that galaxies aren't isolated objects floating in a void. They're embedded in a larger structure, the cosmic web of dark matter and gas that extends throughout space. That web isn't just background. It's the framework that determines where galaxies form, how they evolve, when they merge. The spaces between galaxies are as important to understanding cosmic evolution as the galaxies themselves. There's something beautiful about this process of discovery, isn't there? The way humanity has gradually learned to see what was always there, but hidden. The way each new technique for observation revealed another layer of reality. The way the darkness, when examined carefully enough, turned out to contain multitudes. It's a reminder that absence is often just a limitation of our senses. What we call empty is usually just beyond our ability to perceive directly. And when we build instruments sensitive enough, patient enough, clever enough, we find that emptiness was an illusion. There was always something there. We just hadn't learned how to look for it yet. As you lie there, thinking about these discoveries, you might notice a parallel in your own experience. The silence around you isn't truly silent. It's filled with faint sounds you're not focusing on. The hum of electronics, the whisper of air moving, the subtle creaks of buildings settling. The darkness when you close your eyes isn't pure black. There are faint phosphenes, the ghostly images your visual cortex creates, the play of light and shadow behind your eyelids. In the same way, the intergalactic medium isn't empty. It's full of presences we've learned to detect, full of processes we're beginning to understand. The universe keeps its secrets, but it gives them up eventually to those patient enough to look carefully, to those willing to see past the obvious brightness, to the subtle darkness beyond. The discovery of what lies between galaxies is one of astronomy's great triumphs. It shows that the universe is more connected, more structured, more alive than it first appears. And it reminds us that the most important discoveries often come not from looking at what shines brightest, but from wondering about what doesn't shine at all. When the scientific community began to understand what truly lies between galaxies, the response was a mixture of wonder and bewilderment. The realization that space wasn't empty but filled with invisible matter and energy challenged everything they thought they knew about the cosmos. It was as if they'd been looking at a painting their whole lives, seeing only the bright colors, and suddenly someone showed them the entire canvas, including all the subtle shades they'd missed. The first response was awe. How could they have missed so much? How could the universe hide 95% of its content in forms that don't emit light? The scale of the oversight was staggering. Imagine thinking you understood your house, only to discover that most of it consisted of rooms you couldn't see, filled with furniture you couldn't touch, all invisibly present the entire time. But with awe came questions. So many questions. If dark matter exists, what is it made of? Why doesn't it interact with light? How did it form in the early universe? And dark energy, that mysterious pressure-filling space, what could possibly account for it? Was it a property of the vacuum itself? Some new field or force that physics had never predicted? Or was it a sign that our understanding of gravity needed revision on the largest scales? The questions weren't just about the invisible matter and energy. They were about the structure of the intergalactic medium itself. How did the cosmic web form? Why did matter arrange itself into filaments and voids rather than spreading uniformly through space? What determined which regions became dense and which remained empty? Every answer led to more questions, each question opening new avenues of research. Some scientists responded with excitement. Finally, They thought there were big questions to pursue, fundamental mysteries that went to the heart of how the universe works. The discovery that most of the cosmos was invisible didn't feel like a defeat. It felt like an opportunity. There was so much left to explore, so much left to understand. The universe had just become vastly more interesting. Others responded with frustration. How could they study something they couldn't see? Dark matter didn't emit light, didn't absorb light, didn't seem to interact with ordinary matter except through gravity. Dark energy was even more mysterious, a completely uniform field that affected everything equally. How do you design experiments to test ideas about phenomena that leave such subtle traces? But frustration led to creativity. Scientists began developing new ways to detect the invisible. They built ultra-sensitive detectors deep underground, shielded from cosmic rays, waiting for the rare collision of a dark matter particle with an ordinary atom. They launched space telescopes that could see in X-rays and ultraviolet light, wavelengths where the hot gas in the intergalactic medium might glow faintly. They created massive computer simulations modeling how dark matter and gas would evolve over billions of years, comparing those simulations to observations to test their theories. The response also included a kind of humility. For centuries, humans had assumed that what they could see was most of what existed. Light was the primary tool of astronomy, and if something didn't emit light, it was either absent or unimportant. The discovery of the invisible components of the intergalactic medium shattered that assumption. It revealed that human senses, even augmented by telescopes, captured only a tiny fraction of reality. That humility was uncomfortable, but necessary. It meant acknowledging that the universe was far stranger than anyone had imagined. It meant accepting that decades of astronomical observation had missed the most important components of the cosmos. It meant starting over in some ways, rebuilding understanding from a foundation that included dark matter, dark energy, and all the other invisible presences that filled the spaces between galaxies. There was also wonder at the implications. If space between galaxies was filled with dark matter and dark energy, then those same things existed everywhere. They were here, on Earth, passing through you right now. Dark matter particles might be streaming through your body this very moment, completely unnoticed. Dark energy was pushing on every atom, driving the expansion of space at scales too large to notice in daily life. The invisible wasn't far away. It was intimate, immediate, surrounding you constantly. That realization changed how people thought about their place in the universe. We're not just living on a planet orbiting a star in a galaxy. We're embedded in a cosmic structure that extends far beyond what we can see, connected to everything else through invisible threads of matter and energy. The spaces between galaxies aren't separate from us. They're part of the same continuous medium that includes Earth, the solar system, the Milky Way, and everything else. The first response to discovering what lies between galaxies also included a sense of mystery that hasn't faded with time. Even now, decades after dark matter and dark energy were discovered, we still don't know what they are. We can measure their effects, map their distribution, calculate their influence on cosmic evolution, but we can't explain them in terms of known physics. They remain mysterious, placeholder names for phenomena we detect but don't understand. Some scientists find that mystery frustrating. They want answers, explanations, theories that fit within the existing framework of physics. Others find it thrilling. They see the mystery as evidence that there's still so much to discover, that the universe hasn't given up all its secrets yet, that the greatest breakthroughs might still lie ahead. In public discussions, the response was often one of fascination mixed with confusion. How do you explain dark matter to someone who's never studied physics? How do you convey that most of the universe is invisible? made of things we can't see or touch. The concepts strain ordinary language. We end up using metaphors and analogies that capture part of the truth but miss the subtleties. Yet people responded with interest despite the difficulty. The idea that reality contains hidden layers, that the cosmos is more than it appears, resonates with something deep in human nature. We've always intuited that there's more to the world than meets the eye, that beneath the surface lies greater complexity. The discovery of the invisible intergalactic medium confirmed that intuition on the largest possible scale. The response also included renewed wonder at the universe's beauty. The cosmic web, revealed through observations of how dark matter shapes space, is stunningly elegant. The patterns of filaments and voids, the way matter organizes itself on the largest scales, the delicate balance between expansion and gravity, all of it suggests an underlying order that's both simple and profound. The darkness, when seen properly, isn't chaotic or empty. It's structured, connected, whole. Artists responded by trying to visualize the invisible. Simulations of the cosmic web became sources of inspiration, their flowing filaments and spherical voids, creating images that seemed almost organic. Composers tried to translate the frequencies of cosmic phenomena into music. Writers explored what it might mean to exist in a universe mostly made of things we can't perceive. The discovery sparked creativity across disciplines, proof that scientific findings can inspire more than just more science. Looking back, the first response to discovering what lies between galaxies was really a response to a shift in perspective. It was the moment when humanity realized that brightness isn't the same as importance, that visibility doesn't determine significance, that the quiet spaces matter as much as the loud ones. It was a lesson in humility, in wonder, in the value of looking beyond the obvious. And perhaps most importantly, it was an invitation to explore those dark spaces more carefully, to develop new ways of seeing, to ask questions about things that don't announce themselves with light or heat or sound. The awe and questions that arose from discovering the invisible intergalactic medium haven't faded. If anything, they've deepened as we've learned more. Each answer reveals new questions. Each observation uncovers new mysteries. As you think about that first response, you might notice your own reactions. Wonder at how much can be hidden in plain sight. Questions about what else we might be missing. A sense that reality is deeper and stranger than daily experience suggests. Those responses, that mixture of awe and curiosity, are what drive exploration forward. They're what turn mystery into understanding, slowly, patiently, one discovery at a time. There's a paradox at the heart of the intergalactic medium, a contradiction that seems impossible, yet defines everything about the spaces between galaxies. It's both the emptiest and the fullest place in existence, depending on how you measure. Empty because its density is lower than any vacuum we can create in a laboratory. Full because it contains most of the universe's volume and, therefore, most of what exists. The contradiction isn't a problem to solve. It's the nature of the space itself. Think about what emptiness means. We usually define it as absence, as the lack of something that should be there. An empty room has no people in it. An empty glass holds no water. Emptiness is defined by what's missing. But the intergalactic medium challenges that definition. It's not missing anything. It has exactly what it should have, which is almost nothing per unit volume, but something across vast scales. The contradiction shows up in numbers that don't make intuitive sense. The intergalactic medium might have 1 atom per cubic meter. That's incredibly sparse. For comparison, the air you're breathing has about 10 to the 25th atoms per cubic meter. The intergalactic medium is less dense than Earth's atmosphere by a factor of 10 to the 25. That's emptier than empty by any ordinary standard. And yet, when you add up all that near emptiness across the entire observable universe, you get most of the ordinary matter that exists. The galaxies, bright and dense as they are, contain only a small fraction of the total atoms. Most atoms are in the intergalactic medium, scattered so thinly that they're invisible individually but significant collectively. The majority of existence is in that contradiction, in that space that's empty and full at once. The same paradox applies to dark matter. It doesn't clump as tightly as ordinary matter does. It forms vast halos around galaxies and extended filaments connecting them. Those structures are far more diffuse than galaxies themselves. If you measured the dark matter density at any random point in the intergalactic medium, you'd find very little. But measure it everywhere and add it up, and you get 5 times more mass than all the ordinary matter combined. Empty locally, full globally. Dark energy takes the contradiction even further. It has the same density everywhere. Not just approximately the same, but exactly the same. It doesn't clump or thin or vary with location. Every cubic meter of space, whether inside a galaxy or in the deepest void, contains the same amount of dark energy. That uniformity means that the emptier a region appears to be, the more important dark energy becomes relative to everything else. In the cosmic voids, those enormous regions where galaxies are rare, dark energy dominates completely. The matter density is so low that gravity becomes negligible. What remains is just dark energy, pushing space to expand, creating more volume, which means more dark energy, which drives faster expansion. The voids are the emptiest places in the universe, and the places where the universe's dominant component, dark energy, matters most. Empty yet full indeed. The contradiction creates strange situations. You could travel through the intergalactic medium for millions of light years and encounter almost nothing. A few stray atoms, occasional photons from distant stars, the faint presence of dark matter and dark energy that you can't detect directly. By any local measurement, you'd be in the emptiest environment imaginable. Yet that entire journey would take you through a medium that's completely connected, through a space that's part of a larger structure, through a region that plays a crucial role in cosmic evolution. It's like being in the middle of an ocean. You can look in every direction and see only water, seemingly empty of land or life. Yet that water contains dissolved minerals, supports ecosystems, connects continents, shapes climate. It's empty of the obvious things, land and air and trees, but full of subtle presences that matter enormously. The intergalactic medium is the cosmic equivalent of that ocean, empty of the obvious, full of the subtle. The contradiction also appears in temperature. The intergalactic medium can be cold, just a few degrees above absolute zero in the voids, or hot, millions of degrees near galaxies and along filaments. Hot gas should radiate energy and cool down quickly, but the intergalactic medium is so diffuse that cooling takes billions of years. The atoms are so far apart that they rarely collide, rarely transfer energy, rarely do anything except drift slowly through space. It's hot, but doesn't act hot. It's cold, but still contains thermal energy. Empty, yet full of temperature paradoxes. Scientists struggle with this contradiction when trying to study the intergalactic medium. Normal astronomy relies on detecting light from bright sources, but the intergalactic medium is too diffuse to produce much light. Its atoms are spread so thinly that even when they're hot enough to emit X-rays, the total emission is faint, barely detectable. Observing it requires looking for absence rather than presence, For the shadows it casts on brighter objects rather than light, it produces itself. This creates a methodological challenge. How do you study something that's defined by its near absence? You look for its effects on other things. When light from a distant quasar passes through the intergalactic medium, the gas absorbs specific wavelengths. By studying those absorption patterns, astronomers can map where the gas is, even though they can't see it directly. It's like detecting an invisible object by noticing how it blocks light from something behind it. The contradiction extends to the role the intergalactic medium plays. Despite being nearly empty, it's essential to galaxy formation. Galaxies need gas to form new stars, and they get that gas primarily from the intergalactic medium. The medium acts as a reservoir, supplying matter that eventually becomes stars, planets, and everything else. Without it, galaxies would have exhausted their fuel billions of years ago. The emptiness feeds creation. There's also a temporal aspect to the contradiction. The intergalactic medium wasn't always as empty as it is now. In the early universe, matter was distributed more evenly, and the density everywhere was higher. As the universe expanded, space stretched, and the matter within it became more dilute. The intergalactic medium grew emptier over time, and it's still becoming emptier as expansion continues. Eventually, if current trends continue, it will become even more sparse than it is today, approaching but never quite reaching perfect emptiness. Yet even as it empties, it remains full in another sense. Dark energy, that mysterious pressure driving expansion, stays constant. As space grows, creating more volume, the total amount of dark energy increases. The medium becomes emptier of matter while becoming fuller of dark energy. The contradiction deepens rather than resolves. Philosophers sometimes use the intergalactic medium as an example when discussing the nature of nothingness. Is it truly nothing if it contains scattered atoms, dark matter, dark energy, radiation, or is true nothingness impossible, unphysical? The question isn't just academic. It touches on how we understand existence itself. If even the emptiest region of space contains multiple forms of matter and energy, then maybe pure nothingness doesn't exist in our universe. Maybe everything is varying degrees of fullness. The contradiction also has aesthetic dimensions. When we visualize the universe, we usually show the bright parts, the galaxies and stars. The dark spaces between them appear as background, negative space in the composition. But from another perspective, the darkness is the main subject, and the galaxies are just occasional bright notes in a vast, quiet symphony. Which view is correct? Both. Neither. The contradiction means there's no single right way to see it. Living with this contradiction requires a shift in thinking. We're used to categorizing things as either present or absent, full or empty, something or nothing. But the intergalactic medium exists in a space between those categories. It's present but sparse. It's full but diffuse. It's something but barely so. Learning to think about it means accepting that reality doesn't always fit into neat binary categories. There's something profound about that acceptance. It suggests that many apparent contradictions are really just limitations of our concepts, our language, our ways of thinking. The intergalactic medium isn't paradoxical in itself. It's paradoxical only when we try to force it into categories it doesn't quite fit. Once we accept it on its own terms, the contradiction becomes just description. This is what the space between galaxies is like: empty and full, sparse and significant, nearly nothing and almost everything. As you lie there, contemplating this contradiction, you might notice similar paradoxes in your own experience. The silence around you is full of faint sounds. The darkness behind your eyelids is full of subtle light. The stillness of rest is full of unconscious motion, breathing, heartbeat, the constant activity of cells and molecules. Empty and full coexist everywhere, not just in the intergalactic medium. Perhaps that's why the contradiction doesn't feel strange once you sit with it for a while. It mirrors something fundamental about existence, that absence and presence are often two sides of the same thing, that what matters isn't always obvious or bright or dense, that sometimes the most important things are the ones we almost overlook because they're so diffuse, so subtle, so quietly there. The spaces between galaxies teach that lesson on the grandest scale. They're the universe's way of showing us that emptiness is just another form of fullness, patient and vast. When scientists first realized that the spaces between galaxies weren't empty, they faced a challenge. How do you explain what you can't see? How do you build theories about matter and energy that refuse to reveal themselves through light? The answer came slowly, through careful reasoning, patient observation, and the development of theoretical frameworks that could account for invisible presences. The first theory to address what lies between galaxies was actually about what holds galaxies together. When Fritz Zwicky calculated the mass needed to keep galaxy clusters bound by gravity and found it far exceeded the visible matter, he proposed dark matter. But what was it? The early theories suggested it might be ordinary matter in dark forms, black holes, brown dwarfs, planets, anything that had mass but didn't shine. This idea, called MACOs for massive compact halo objects, seemed reasonable. After all, we knew such objects existed. Why couldn't there be enough of them to account for the missing mass? But as observations improved, MACOs fell out of favour. There simply weren't enough dark stellar remnants to explain the amount of missing mass. The universe contained far more dark matter than could be explained by ordinary matter in dark form. That led to the next theory. If dark matter wasn't ordinary matter being dark, maybe it was extraordinary matter. Particle physicists proposed various candidates. WIMPs, weakly interacting massive particles, would have mass but interact only through gravity and the weak nuclear force, making them essentially invisible. Axions, hypothetical particles much lighter than any known particle, could fill space in vast numbers, adding up to significant mass despite their individual lightness. These theories made specific predictions. If dark matter consisted of WIMPs, experiments might detect them through rare collisions with ordinary atoms. If it was axions, sensitive instruments might detect their interactions with strong magnetic fields. Decades of experiments have searched for these signals. So far, nothing definitive has been found. The theories remain plausible but unconfirmed, keeping dark matter's true nature mysterious. The development of theories about dark energy followed a different path. When astronomers discovered that the universe's expansion was accelerating, they initially doubted their own results. The observations were at the edge of what was measurable, and systematic errors seemed more likely than a revolutionary discovery. But as more data accumulated from multiple independent teams, the conclusion became unavoidable. Something was pushing space apart. The simplest theory to explain acceleration was Einstein's cosmological constant. When Einstein first developed general relativity, he included a term representing energy inherent to empty space itself. He later removed it, calling it a blunder, but the mathematics remained valid. If empty space had a small, positive energy density, it would create a kind of repulsive gravity, pushing everything apart. Dark energy could be that cosmological constant, resurrected decades after Einstein abandoned it. But the cosmological constant theory had a problem. When physicists tried to calculate what that constant's value should be based on quantum mechanics, they got a number vastly larger than observed, off by about 120 orders of magnitude. It's the worst theoretical prediction in the history of physics. Something was deeply wrong, either with the calculation or with the understanding of how quantum mechanics and gravity interact. Alternative theories proposed that dark energy wasn't constant but varied over time. These quintessence models suggested a new field filling space, something like the field thought to drive cosmic inflation in the early universe, but weaker and operating now. If dark energy changed slowly over billions of years, it might explain why it started dominating the universe relatively recently, rather than always or never. Yet other theories questioned whether dark energy existed at all. Maybe instead of a new form of energy, the acceleration indicated that gravity works differently on cosmic scales than Einstein's equations predict. Modified gravity theories adjusted general relativity to reproduce the observed acceleration without invoking dark energy. These theories made different predictions about the universe's structure and evolution, predictions that observations could test. The theories about the intergalactic medium's ordinary matter are less exotic but no less important. Cosmologists developed detailed models of how gas flows through the cosmic web, how it heats and cools, how it falls into galaxies and gets expelled by supernovae and black holes. These models explained why the intergalactic medium has the density and temperature it does, how it evolved from the early universe's nearly uniform state to the structured web we see today. One key theoretical insight was understanding the different phases of the intergalactic medium. Some regions are cold and diffuse, with gas at temperatures of tens of thousands of degrees. Others are hot and slightly denser, with gas heated to millions of degrees by falling into gravitational wells or by radiation from nearby galaxies. The theory predicted that most of the ordinary matter should be in this warm-hot phase, too diffuse to see easily but detectable through its absorption of ultraviolet and X-ray light. Theories also addressed the chemical composition of the intergalactic medium. In the early universe, only hydrogen and helium existed. Heavier elements formed in stars through nuclear fusion. When those stars exploded as supernovae, or when galaxies drove two winds into their surroundings, they scattered those heavy elements into space. Theories predicted that the intergalactic medium should show chemical enrichment, with traces of carbon, oxygen, and iron mixed into the hydrogen. Observations confirmed this prediction, finding exactly the pattern of enrichment the theory suggested. The intergalactic medium near galaxies showed more heavy elements, while gas in the deepest voids remained nearly pristine. This confirmed that galaxies weren't isolated systems, but continuously exchanged matter with their surroundings, polluting the intergalactic medium with the products of their stellar populations. The theory of the cosmic web's formation brought all these ideas together. Computer simulations, starting from the nearly uniform conditions of the early universe and following billions of years of evolution, reproduced the observed structure. Dark matter clumped first, forming filaments under gravity's influence. Ordinary gas fell into those filaments, heating as it accumulated. Galaxies formed where the filaments intersected, in regions dense enough for gas to cool and collapse into stars. These simulations showed that the pattern of filaments and voids emerged naturally from the laws of physics. Gravity amplified tiny initial variations in density until they became the cosmic web. The intergalactic medium wasn't just passive background. It was an active participant, its gas flowing along dark matter filaments, its pressure resisting collapse in some regions while allowing it in others. The theories also predicted how the intergalactic medium would evolve in the future. As dark energy continues to drive accelerated expansion, the distance between galaxy clusters will grow, The filaments connecting them will stretch and thin. Eventually, the cosmic web will dissolve as expansion overcomes gravity's ability to hold it together. In the far future, only local groups of galaxies will remain bound, isolated islands in an otherwise empty universe. This prediction gives the current era special significance. We live at a time when the cosmic web is still visible, when the intergalactic medium still connects galaxy clusters, when the universe's structure is still apparent. Trillions of years from now, observers in distant galaxies, if any exist, won't be able to see that structure. The evidence will have expanded beyond their horizon. They'll live in a universe that seems much smaller and simpler than the one we can observe. The development of these theories represents one of science's great achievements, building understanding of phenomena that can't be seen directly, that leave only the faintest traces, that operate on scales far beyond human experience. Each theory made predictions, observations tested those predictions, and gradually the picture became clearer. Not complete, not final, but clearer. What makes these theories powerful isn't that they explain everything. They don't. Dark matter's identity remains unknown. Dark energy's nature is mysterious. Many details of how gas flows through the intergalactic medium are still being worked out, but the theories provide a framework, a way of organizing observations, a structure for thinking about what lies between galaxies. They also reveal something about the scientific process. We can understand phenomena we can't see. We can build accurate models of invisible things through their effects on visible things. We can follow gravity's logic, thermodynamics principles, quantum mechanics rules to places no telescope will ever reach. Theory extends our perception beyond our senses, allowing us to explore regions that will forever remain unvisitable. As you think about these theories, these attempts to make sense of darkness, you might notice how similar the process is to understanding anything subtle. We often can't see causes directly. We can only see their effects. We build models, test predictions, refine understanding. The intergalactic medium just takes that process to an extreme where almost everything is invisible and almost every measurement is indirect. But the theories work. They make predictions that observations confirm. They explain patterns that would otherwise seem random. They turn what could have remained mysterious into something comprehensible, if not yet fully understood. And in doing so, they transform the darkness between galaxies from an absence into a presence, from nothing into a richly structured medium where most of the universe's story unfolds. When we talk about the spaces between galaxies, numbers become almost meaningless. The distances are so vast that even light, travelling at 300,000 kilometers per second, takes millions or billions of years to cross them. Our everyday experience gives us no reference for such scales. We can say the words, but can we truly grasp what they mean? Let's start with something more familiar and work our way outward. The moon is about 384,000 kilometers from Earth. Light takes just over a second to cover that distance. In human terms, it's far, but not incomprehensibly so. We've sent astronauts there. We can imagine the journey, even if we'll never take it ourselves. The sun is much farther, about 150 million kilometers away. Light takes 8 minutes to travel from the sun's surface to Earth. That's our first step into truly cosmic distances. If the sun suddenly vanished, we wouldn't know for 8 minutes. The light showing us a sun that exists was actually a sun from 8 minutes ago. Distance and time start to merge. The nearest star beyond the sun, Proxima Centauri, is 4.2 light-years away. That's about 40 trillion kilometers, a distance so large that even moving at the speed of light, unreachable for anything with mass, the journey would take more than 4 years. Our fastest spacecraft, moving at a mere fraction of light speed, would take thousands of years to reach it. The distance has crossed from the merely far to the practically infinite. But that's just the nearest star. The Milky Way, our home galaxy, is about 100,000 light-years across. Light leaving one edge takes 100,000 years to reach the other. The galaxy we live in is so large that light from most of it takes longer to reach us than all of recorded human history. When we look at stars on the far side of the galaxy, we see them as they were when early humans were learning to use fire. And yet, compared to the distances between galaxies, even the Milky Way is small. The nearest large galaxy, Andromeda, sits about 2.5 million light-years away. The light we see from it tonight began its journey before the first humans walked upright. The ancestors who would eventually become us hadn't even evolved yet when that light started moving through space. Every photon from Andromeda is a time traveler, carrying messages from an ancient past. That's our cosmic neighborhood, the local group of galaxies. Within a few million light-years, there are dozens of galaxies gravitationally bound to each other. But step back farther, and the distances grow impossibly larger. The Virgo cluster, a large collection of galaxies, is about 55 million light-years away. The Coma cluster is over 300 million light-years distant, and the observable universe extends for about 46 billion light-years in every direction. Wait, you might think 46 billion light-years, but the universe is only about 13.8 billion years old. How can light have travelled farther than the age of the universe? The answer is expansion. While light has been travelling toward us, space itself has been stretching, carrying its source farther away. The most distant galaxies we can see emitted their light when the universe was young, but they've since moved much farther away due to cosmic expansion. These numbers are so large they stop feeling real. What does it mean for something to be billions of light years away? How do we process that information emotionally, not just intellectually? Perhaps the only honest answer is that we can't, not really. Our brains evolved to understand distances we could walk, run, or throw a stone across. Cosmic distances exist in a different realm entirely, comprehensible through mathematics but not through intuition. The spaces between galaxies represent most of this distance. If you could shrink the Milky Way down to the size of a coin and place it on a map, Andromeda would be several cities away, but the space between them, that vast gulf, would be mostly empty of matter, filled only with the faint, diffuse presence of the intergalactic medium. Scale it up to the real distances, and you're looking at millions of light years of near nothingness, broken occasionally by a stray atom or photon. When astronomers map galaxy clusters, they find typical separations of tens of millions of light years between clusters. The filaments of the cosmic web can stretch for hundreds of millions of light years, thin threads of slightly elevated density connecting the bright nodes where galaxies gather, and the voids between filaments, those enormous empty regions, can span hundreds of millions of light years in diameter. You could fit thousands of Milky Ways end to end across a single void and still have room left over. Trying to visualize these scales is almost futile, but let's try anyway. Imagine you could travel at the speed of light, moving as fast as physics allows anything to move. Starting from Earth, you'd reach the moon in 1 second, the sun in 8 minutes, Proxima Centauri in 4 years, the far edge of the Milky Way in 100,000 years, Andromeda in 2.5 million years, and if you wanted to cross just one cosmic void, you might travel for hundreds of millions of years without encountering a single galaxy. At those scales, even light seems slow. The universe is so large that light itself, the fastest thing that exists, takes eons to cross it, and the distances are growing. Every second, the space between distant galaxies increases by thousands of kilometers, not because they're moving through space, but because space itself is expanding, adding more distance between everything not bound together by local gravity. This expansion means that the farthest galaxies we can see are moving away from us faster than light. That sounds like it violates relativity, which says nothing can move faster than light through space. But the galaxies aren't moving through space that fast. Space between us and them is expanding so rapidly that the distance increases faster than light can cross it. They're receding beyond the reach of light, slipping past a cosmic horizon beyond which we'll never be able to see them, no matter how long we wait. The scale of the universe creates a kind of isolation. Even if we could somehow send a signal to another galaxy traveling at light speed, it would take millions or billions of years to arrive. Any response would take just as long to return. The conversation would unfold on timescales longer than civilizations typically last. The distances don't just separate galaxies in space, they separate them in time as well, making meaningful interaction impossible. And yet, despite these incomprehensible distances, everything remains connected. The same laws of physics apply everywhere. The same forces operate across all scales. The light from distant galaxies, though ancient by the time it reaches us, still carries information we can decode. The gravitational influence of massive structures can be felt across hundreds of millions of light years. The expansion of space affects everything equally, from neighboring galaxies to the most distant ones we can see. There's something both humbling and comforting about these scales. Humbling because they reveal how tiny our corner of the universe is, how brief our existence is compared to cosmic timescales, how limited our direct reach will always be, but comforting because they remind us that we're part of something vast and ancient, that the atoms in our bodies have travelled across these immense distances over billions of years, that we're connected to everything else through the same fundamental forces and fields. The scale of the spaces between galaxies also puts our own existence into perspective. Life exists, as far as we know, on a single planet orbiting a single star in one galaxy among hundreds of billions. We occupy an infinitesimally small fraction of space and have existed for an infinitesimally small fraction of time. And yet, somehow, from that tiny vantage point, we've measured the distances to other galaxies, calculated the universe's age, and begun to understand what fills the vast spaces between everything. That's remarkable when you think about it. We can't travel to other galaxies. We never will, barring physics we don't yet know about. But we can study them, we can understand them, we can measure distances we'll never cross, and perceive light from sources we'll never visit. Our minds can reach across billions of light years even though our bodies are confined to a single small world. As you lie there, contemplating these scales, you might feel very small, and you are, compared to the cosmic distances we're discussing. But you're also part of the same continuous universe that extends across all those light years. The same forces that separate galaxies also hold you together. The same expansion that stretches space between clusters also exists here. Though it's too weak to notice against the local pull of gravity, you're not separate from the cosmic scale. You're embedded in it, a local expression of the same patterns that play out across billions of light years. The distances between galaxies define the universe's character. They create the dark spaces where most of existence occurs. They determine how galaxies evolve in relative isolation or in crowded clusters. They set the timescale for cosmic processes, ensuring that change happens slowly enough for structures to form, but fast enough that the universe remains dynamic. Without those vast separations, the cosmos would be fundamentally different, perhaps impossible. So when we talk about scale, about the distances that separate galaxies, we're really talking about the architecture of existence itself. The spacing isn't random. It emerged from the universe's initial conditions and evolved according to the laws of physics. The fact that galaxies sit millions of light years apart rather than billions or thousands is a consequence of how matter distributed itself in the early universe, how gravity gathered it into structures, how expansion stretched everything over time. Understanding that scale, even imperfectly, changes how you see the night sky. Those points of light aren't just pretty decorations. They're entire galaxies, each containing billions of stars, separated from us and from each other by distances so vast that calling them vast doesn't capture it. The darkness between them isn't empty. It's filled with the intergalactic medium, with dark matter, with dark energy, with the slow processes that connect everything across time and space. The scale is beyond human comprehension in a literal sense. We can't truly grasp it intuitively, but we can appreciate it. We can feel the weight of those numbers, the enormity of the distances, the patience of light travelling for millions of years, and in that appreciation, we find our place. Not at the centre, not at the edge, but somewhere in the middle of something so large it makes ordinary adjectives meaningless. The spaces between galaxies stretch infinitely in our experience, even though they're finite in reality. And in that stretch, in those unimaginable distances, the universe finds room to be itself, vast, patient, and full of quiet wonders. When astronomers first began mapping the positions of galaxies across the sky, they expected to find them distributed more or less randomly, like stars scattered across the night. But as the surveys grew larger and more detailed, a pattern emerged. Galaxies weren't scattered randomly at all. They were arranged in structures, great interconnected filaments, forming a vast three-dimensional web that stretched across hundreds of millions of light years. This cosmic web is one of the most beautiful patterns in nature, though it's so large that seeing it requires mapping millions of galaxies. Imagine looking at a single square centimetre of fabric. You see threads, knots, maybe a pattern in the weave. Now imagine that fabric stretched across the entire observable universe, with galaxies marking the intersections of threads and enormous voids opening up in the spaces between them. That's the cosmic web, the largest known structure in existence. The web formed gradually over billions of years through gravity's patient work. In the early universe, matter was distributed almost uniformly, with only tiny variations in density from place to place. These variations, imprinted during the first moments after the Big Bang, were incredibly small, differences of only 1 part in 100,000. But gravity amplifies differences. Regions that were slightly denser attracted more matter from their surroundings, becoming denser still. Regions that were slightly less dense lost matter to their neighbours, becoming emptier. Over time, this process created a network of overdense regions surrounded by underdense ones. The overdense regions formed filaments, thin threads of elevated density where matter accumulated. Where filaments intersected, the density was highest, and these nodes became the sites of galaxy clusters. Between the filaments, vast voids opened up, regions where the density fell below average and continued falling as matter drained toward the porose filaments. The cosmic web wasn't built from ordinary matter alone. In fact, ordinary matter played a relatively minor role. The web's structure is primarily determined by dark matter, that invisible substance that makes up most of the universe's mass. Dark matter clumped first, forming halos and filaments that served as gravitational scaffolding. Ordinary matter, in the form of hydrogen and helium gas, fell into these dark matter structures, cooling and condensing to form galaxies along the filaments and at their intersections. Computer simulations of cosmic structure formation show this process beautifully, starting from nearly uniform initial conditions and evolving forward according to the laws of gravity. The simulations produce structures that look remarkably like what astronomers observe. The same pattern of filaments and voids emerges naturally, confirming that the cosmic web is a consequence of gravity acting on matter over billions of years. No special initial conditions or fine-tuning required, just gravity and time. The filaments themselves are extraordinary structures. They can stretch for hundreds of millions of light years, yet they're relatively narrow, perhaps tens of millions of light years across. Think of them as cosmic highways, channels along which matter flows from the voids toward the galaxy clusters. The density along a filament is higher than average, but not dramatically so. It's enough to guide the flow of gas and to serve as locations where galaxies form, but not enough to make the filaments shine brightly on their own. Observing the cosmic web directly is challenging because most of it is made of dark matter and diffuse gas, neither of which emits much light. Astronomers map it primarily by plotting galaxy positions. Where galaxies cluster together, there must be an underlying filament of dark matter holding them in place. Where galaxies are rare or absent, there must be a void. By mapping millions of galaxies, they can trace out the web structure, seeing the filaments as concentrations of galaxies and the voids as regions where galaxies are sparse. Recent observations have begun to detect the gas within the filaments as well. When light from distant quasars passes through a filament, the gas absorbs specific wavelengths, leaving fingerprints in the quasar's spectrum. By studying many quasars, astronomers can map where the gas lies and how dense it is. The results confirm what simulations predicted. The intergalactic medium isn't uniformly distributed but follows the cosmic web structure, denser along filaments and thinner in voids. Some observations have even detected faint glows of light from the filaments themselves. The gas there, heated by falling into the dark matter's gravitational wells or by radiation from nearby galaxies, emits X-rays and ultraviolet light. These signals are incredibly faint, requiring long exposures and sensitive instruments to detect, but they provide direct evidence of the hot gas. Threading through the cosmic web, the nodes of the web, where filaments intersect, are special places. These are the densest regions in the universe, locations where multiple filaments converge and deposit their matter. Galaxy clusters form at these intersections, great collections of hundreds or thousands of galaxies bound together by their mutual gravity. The largest clusters can contain as much mass as a quadrillion suns, most of it in the form of hot gas and dark matter rather than in stars. Between the filaments lie the voids, enormous regions where galaxies are rare. These voids aren't completely empty. They contain some isolated galaxies and diffuse gas, but their average density is much lower than elsewhere. The largest voids can span hundreds of millions of light years, spherical or elliptical regions surrounded by the walls and filaments where galaxies cluster. They're the quietest places in the universe, regions where very little happens and where the expansion of space dominates over gravity's pull. The cosmic web creates a kind of hierarchy in the universe's structure. At the smallest scales, stars cluster into galaxies. Galaxies cluster along filaments. Filaments connect at nodes to form superclusters, and superclusters are separated by voids. Each level of structure is embedded in the next larger one, creating a nested pattern that extends from individual stars to the observable universe itself. This hierarchy has profound implications for how the universe evolved. Galaxies don't form in isolation. They form along filaments, where gas can flow in from the surrounding regions. The filaments themselves channel matter toward the nodes, feeding the growth of massive galaxy clusters. The voids, emptier than average, serve as sources of matter that drains toward the denser regions. Everything is connected through this web. Everything influences everything else through gravity's long reach. The cosmic web also influences how galaxies themselves evolve. Galaxies in dense regions, along thick filaments or within clusters, experience frequent interactions with neighbors. They collide, merge, and strip matter from each other. These interactions trigger bursts of star formation and feed the supermassive black holes at galaxy centers. Over time, cluster galaxies tend to exhaust their gas supplies and stop forming new stars, becoming red and dead, dominated by old stellar populations. Galaxies in the voids or along thin filaments evolve differently. With fewer neighbors and less interaction, they retain their gas longer and form stars more gradually. They tend to be smaller, bluer, and more gas-rich than cluster galaxies. Their isolated existence allows them to develop more slowly, unperturbed by the violent interactions common in denser regions. The cosmic web structure thus determines not just where galaxies are, but what kinds of galaxies exist in different locations. Scientists study the cosmic web to understand the universe's composition and evolution. The web structure depends on how much dark matter exists, how much dark energy there is, and how the universe has expanded over time. By measuring the web's properties, the typical size of voids, the length of filaments, the mass of clusters, astronomers can constrain these fundamental parameters. The cosmic web becomes a laboratory for testing cosmological theories. Recent surveys have mapped the cosmic web in unprecedented detail. Projects like the Sloan Digital Sky Survey have catalogued positions and distances for millions of galaxies, creating three-dimensional maps that reveal the web's structure clearly. When these maps are visualized, they show a striking pattern, a delicate lacework of filaments surrounding bubble-like voids, all interconnected in a continuous network that fills space. The beauty of these images is undeniable. They look almost organic, like neural networks or blood vessels or root systems. The similarity isn't coincidental. Many complex systems, from biological to cosmic, organize themselves into networks because networks are efficient at distributing matter and energy. The cosmic web structure reflects the most efficient way for gravity to organize matter across vast scales, creating connections that minimize gravitational potential energy. There's something profound about discovering that the universe has this hidden structure. For most of history, the cosmos seemed chaotic on large scales, just a random distribution of stars and galaxies. But the cosmic web reveals an underlying order, a grand pattern that emerges naturally from simple laws of physics. It's a reminder that nature often organizes itself, that order arises spontaneously from apparent randomness when the right forces operate over sufficient time. The web also connects everything in a literal sense. Follow a filament from one galaxy cluster to another, and you'll trace a continuous path through slightly elevated density, through regions where galaxies are more common, where gas flows along gravitational channels, where dark matter forms invisible bridges. The spaces between galaxies aren't barriers, they're parts of a connected network, regions that facilitate communication between the bright nodes, even if that communication happens slowly, over millions of years. As you think about the cosmic web, imagine yourself within it. The Milky Way sits on a filament, part of a structure called the local sheet, which connects our local group to larger structures like the Virgo cluster. We're not in a void or at a major node, we're somewhere in between, on one of the countless threads that make up the web. From our position, we can see the web stretching around us, though it takes powerful telescopes and careful observation to trace its full extent. That perspective is grounding. We're not at the center of anything special, but we're not isolated either. we're part of the structure, embedded in the same web that connects everything else. The same forces that shaped the cosmic web on the largest scales also shaped our galaxy, our solar system, ultimately us. We're local expressions of a pattern that extends across the entire observable universe. The cosmic web will continue to evolve. As the universe expands and dark energy becomes increasingly dominant, the filaments will stretch and thin. Eventually, in the far future, the web may dissolve entirely as expansion overcomes the gravity holding structures together. But for now, in this cosmic epoch, the web is visible and vibrant, a testament to gravity's ability to create order from near uniformity, to build the largest structures in existence from the simplest beginnings. It's the universe's way of organizing itself, of creating the framework within which galaxies form, evolve, and eventually fade. And it's beautiful in its own vast, patient way. Within the cosmic web, between the bright filaments where galaxies gather, lie regions so empty they seem to defy description. These are the cosmic voids, enormous spherical or elliptical volumes where almost nothing exists. They're the largest individual structures in the universe, some spanning hundreds of millions of light years across. To float in the center of one would be to experience isolation on a scale that's hard to even imagine. The voids aren't completely empty. A point worth emphasizing: they do contain some galaxies, typically small, isolated systems that are rare enough to make the void seem vacant by comparison. They contain the intergalactic medium, though at densities even lower than average, just a scattered atom here and there across vast volumes. They contain dark matter, spread diffusely through the region, and they contain dark energy, which fills all of space equally, and actually dominates the voids more than anywhere else, because there's so little matter to compete with it. But despite these presences, the voids are fundamentally different from other cosmic regions. If you measured the density of matter in a typical void, you'd find it's only 10 to 20% of the cosmic average. That might not sound like a huge difference, but in a universe where structure forms through gravitational amplification of small density differences, it's enormous. The voids are regions where gravity's attractive force is so weak that expansion dominates, where space stretches faster than matter can clump, where the universe reveals what it looks like when almost nothing interrupts its natural tendency to grow. The largest known voids have names that hint at their enormity. The Boötes void, discovered in 1981, spans about 330 million light-years across. Inside it, astronomers have found only about 60 galaxies, where a region of that size elsewhere might contain thousands. The Eridanus supervoid is even larger, spanning about 1 billion light-years. These aren't just empty spots, they're fundamental features of the universe's structure, as important to understanding the cosmos as the galaxies themselves. How did the voids form? The process is the mirror image of how filaments formed. In the early universe, regions that were slightly less dense than average expanded faster than their surroundings. As they expanded, they became relatively emptier, losing what little matter they had to neighboring denser regions. Over billions of years, this process created vast underdense regions, surrounded by walls of galaxies, marking the boundaries where matter accumulated as it drained from the voids. Computer simulations show this process clearly. Start with a nearly uniform distribution of matter, add tiny random variations in density, and let gravity work. The denser regions pull in matter, forming filaments and clusters. The less dense regions lose matter, becoming voids. The result is a foam-like structure, with galaxies concentrating along the surfaces of bubble-like voids. The voids. aren't carved out by anything. They're simply the regions that gravity left behind as it gathered matter elsewhere. The temperature inside a void is notable. With so little matter and so few nearby sources of radiation, the gas that does exist there is among the coldest in the universe, perhaps just a few degrees above absolute zero. The photons from the cosmic microwave background pass through unimpeded, but they provide almost no heat. Any atoms present would drift slowly, rarely colliding with anything else, cooled by billions of years of expansion with almost nothing to warm them. Yet near the edges of voids, conditions can be different. Where the void meets the surrounding filaments, the density rises. Gas from the void might be slowly draining toward those denser regions, heating as it falls into gravitational wells. Some void galaxies might be forming stars, providing local sources of heat and radiation. The boundaries aren't sharp walls, but gradual transitions where the density slowly increases from the void's interior toward the cosmic average. Standing in thought at the center of a void, you would see a night sky unlike anything visible from Earth. The nearest bright galaxy might be 100 million light-years away, appearing as just a faint smudge even through a powerful telescope. In every direction, the view would be similar. Distant, dim, scattered galaxies, far too faint to cast any meaningful light. You'd be surrounded by darkness so complete that the cosmic microwave background, that faint all-sky glow from the Big Bang, might be the brightest thing you could detect. The isolation would be more than just visual. Any signal you tried to send to another galaxy would take millions of years to arrive, traveling through space that contains almost nothing to interact with. There would be no nearby stars to cast shadows, no gravitational disturbances from passing structures, no indication that anything was happening anywhere nearby. Time would seem to pass differently somehow, each moment identical to the last, with no change or motion to mark its passage. This isolation makes voids ideal for certain kinds of astronomical observations. Without much nearby matter to emit radiation or distort signals, observations through voids would be remarkably clean. Light from distant galaxies would pass through with minimal absorption or scattering. Gravitational lensing, the bending of light by matter, would be minimal. In principle, a telescope located in a void would have an exceptionally clear view of the distant universe, unobstructed by nearby structures. Of course, the practical challenges of placing anything in a void are overwhelming. The distances involved make it impossible with any current or foreseeable technology. But the thought experiment reveals something interesting. The voids aren't just empty spaces between the interesting regions. They're regions with their own unique properties, places where the universe behaves differently than in denser areas. Understanding voids is as important as understanding filaments or clusters. The existence of voids also tells us something fundamental about the universe's geometry. They show that space is relatively flat on large scales. If the universe had significant curvature, voids would be distorted in predictable ways. The fact that they're roughly spherical or elliptical, following simple geometric shapes, confirms that space behaves like Euclidean geometry on cosmic scales. The universe's large-scale structure fits on a flat canvas. Voids also serve as laboratories for studying dark energy. Because matter is so sparse in voids, dark energy's effects dominate there more than anywhere else. Observations of how voids evolve, how fast their boundaries are receding, how their size distribution changes over time, all provide information about dark energy's properties. If dark energy varied in strength or changed over time, voids would reveal those changes through subtle effects on their structure. Some scientists study what they call void galaxies, the rare systems that form within these empty regions. These galaxies tend to be small, blue, and actively forming stars, different from galaxies in denser environments. They've experienced less interaction with neighbours, less stripping of gas by encounters, or ram pressure from moving through hot intracluster gas. In some ways, they're pristine, evolving more slowly and predictably than galaxies in busier regions. The psychology of contemplating voids is interesting. They represent ultimate emptiness, regions where even the sparse intergalactic medium becomes sparser, where the distance between objects reaches its maximum. Yet they're not frightening or threatening. They're peaceful. They're the universe at its most relaxed, untroubled by gravitational interactions or energetic events. The voids are where the cosmos simply expands, quietly and steadily, without drama or urgency. There's a philosophical dimension too. The voids remind us that most of existence is absence rather than presence, at least by certain measures. Most of the universe's volume is void. Most of space contains almost nothing. The bright, interesting, active regions, the galaxies and stars we focus on, are exceptions. The rule is emptiness. The baseline is void. Everything we consider normal and interesting is actually unusual, a local concentration of matter in a universe that's mostly space. This inversion of perspective can be disorienting. We tend to think of galaxies as the main event and voids as gaps between them. But by volume, the voids are the main event. Galaxies are just occasional interruptions in the vast emptiness. If the universe has a natural state, it's void, not galaxy. What we call empty is actually the norm. What we call full is the anomaly. As expansion continues and dark energy drives the universe to grow faster, the voids will become more dominant. The filaments, connecting, galaxies will stretch and thin. The distances between clusters will grow until most clusters disappear beyond each other's cosmic horizons. In the far future, the universe will consist almost entirely of void-like regions, with occasional isolated galaxy groups drifting alone in the vastness. The voids are a preview of the universe's ultimate fate, but that's billions or trillions of years away. For now, the voids coexist with the cosmic web's filaments and nodes, forming one part of the larger pattern. They're not separate from the structure. They're integral to it. Without voids, there would be no contrast to make the filaments visible. Without the empty regions, the concept of structure wouldn't have the same meaning. The voids define the full regions by being their opposite. When astronomers map the universe's large-scale structure, the voids show up as dark bubbles surrounded by bright walls of galaxies. The images are striking. They look like foam or bubbles in a bathtub, spheres of darkness separated by thin films of light. It's a pattern that appears at many scales in nature, from soap bubbles to biological cells to the structure of the cosmos itself. There's something universal about this geometry, something efficient about organizing space into cells separated by walls. Thinking about the great voids, you might feel a kind of calm. They represent the universe stripped down to essentials: space, expansion, darkness, and time. No complications, no interactions, no energy beyond what's intrinsic to space itself. They're places where nothing happens, and that nothingness is its own kind of completeness. The voids don't lack anything. They're exactly what they should be, given the universe's laws and history. So the great voids aren't absences or flaws in the cosmic structure. They're features, important and meaningful ones. They show us what the universe looks like when matter is minimal, when gravity is weak, when expansion dominates. They're the canvas on which everything else is painted, the background that makes the foreground visible, and they're patient, unchanging on human timescales, growing slowly as the universe expands, waiting in darkness for billions of years without urgency or purpose. Just empty space being itself. Of all the things that fill the spaces between galaxies, perhaps the most important is also the most mysterious. Dark matter, the invisible substance that makes up most of the universe's mass, forms the hidden scaffolding that holds everything together. We can't see it. We can't touch it. We've never directly detected a single particle of it. Yet without dark matter, galaxies as we know them couldn't exist, and the cosmic web would collapse into something unrecognizable. The evidence for dark matter is overwhelming, even though the substance itself remains elusive. It shows up in how galaxies rotate, spinning too fast to hold together if visible matter were all they contained. It appears in how galaxy clusters move, their members orbiting far faster than the gravity of visible matter could explain. It reveals itself through gravitational lensing, bending light from distant galaxies in patterns that require more mass than we can see. Every independent line of evidence points to the same conclusion. Most of the universe's matter is invisible. That invisible matter isn't concentrated just inside galaxies. It fills the spaces between them, forming vast halos that extend far beyond where any stars shine. These halos merge into filaments, the same filaments that define the cosmic web's structure. Dark matter provides the gravitational framework, the skeleton on which ordinary matter hangs like decoration. The intergalactic medium follows dark matter's lead, flowing along the invisible filaments, accumulating where dark matter is densest. Computer simulations of structure formation depend critically on dark matter. Start with the conditions of the early universe. Let dark matter evolve, according to gravity's laws, and watch as it forms a web of filaments and nodes. Then add ordinary matter, which falls into the dark matter's gravitational wells, cooling and forming galaxies along the filaments. The simulations match observations remarkably well, reproducing the cosmic web structure, the distribution of galaxies, even details like how many satellite galaxies large systems should have. But what is dark matter? That's the profound mystery. It clearly has mass and exerts gravity. It clumps under its own gravitational attraction, but it doesn't emit, absorb, or scatter light in any detectable way. It doesn't seem to interact with ordinary matter, except through gravity. These properties suggest it's not made of the same particles that compose atoms, stars, and planets. It must be something else, some new form of matter that physics hasn't yet discovered. Various candidates have been proposed. WIMPs, weakly interacting massive particles, would be heavy particles that feel gravity and perhaps the weak nuclear force, but nothing else. Experiments have searched for them in deep underground laboratories, waiting for rare collisions with ordinary atoms, but so far none have been definitively detected. Axions, much lighter hypothetical particles, could swarm through space in vast numbers. Their individual masses so small that they'd add up to the required total only because there are so many of them. Other theories suggest dark matter might be primordial black holes, formed in the early universe rather than from collapsing stars, or sterile neutrinos, particles similar to ordinary neutrinos but even more reluctant to interact with matter, or something completely new, a type of particle or field that doesn't fit into our current understanding of physics at all. The lack of direct detection keeps all these possibilities open while ruling out none of them definitively. What we do know is how dark matter behaves on large scales. It forms halos around galaxies, with density decreasing as you move outward from the center. These halos can extend for hundreds of thousands of light years, far beyond the visible galaxy. In the spaces between galaxies, dark matter follows the filaments of the cosmic web, creating threads of elevated density that guide ordinary matter's motion. The distribution isn't uniform. It's structured, following the same patterns gravity creates in any self-gravitating system. The dark matter in the intergalactic medium plays a crucial role in cosmic evolution. When ordinary gas flows along a filament toward a galaxy, it's actually following dark matter's gravitational pull. The gas heats up as it falls into the dark matter's potential well, sometimes reaching temperatures of millions of degrees. This hot gas can either cool and fall into galaxies to form new stars, or it can be heated further by supernova explosions and pushed back out into intergalactic space. Either way, dark matter determines where and how the gas moves. Dark matter also determines where galaxy clusters form. Clusters appear at the nodes of the cosmic web, where multiple filaments of dark matter intersect. The combined mass creates a deep gravitational well that captures galaxies, hot gas, and more dark matter. Over time, clusters grow larger as additional matter falls in along the filaments. The most massive clusters today mark the deepest dark matter concentrations in the universe, regions where gravity is strong enough to bind thousands of galaxies together. Observations of gravitational lensing provide some of the clearest evidence of dark matter's distribution. When light from distant galaxies passes near a massive cluster, the cluster's gravity bends the light's path, creating distorted or multiple images of the background galaxies. By studying these distortions, astronomers can map where the mass is, even if they can't see it directly. The results consistently show that clusters contain far more mass than their visible matter can account for, and that mass is distributed in extended halos consistent with dark matter simulations. Some of the most famous examples come from colliding galaxy clusters. When two clusters merge, their galaxies and dark matter pass through each other relatively unimpeded, since both are collisionless on large scales. But the hot gas in each cluster collides, creating shock waves that slow it down. In these systems, gravitational lensing reveals that most of the mass is displaced from the hot gas, having moved ahead with the galaxies. This spatial separation of visible and invisible mass provides striking visual evidence that dark matter exists as a separate component. The Bullet cluster is perhaps the most celebrated example. Two galaxy clusters collided billions of years ago, passing through each other at high speed. The galaxies in each cluster continued mostly undisturbed. The hot gas collided and slowed, emitting X-rays from the shock. But gravitational lensing shows that most of the mass didn't slow down. It's displaced from the gas, aligned with the galaxies. The only reasonable explanation is that dark matter, which doesn't interact with itself strongly, passed through unimpeded while ordinary matter collided and heated. Despite all this evidence, dark matter remains profoundly mysterious. We know it's there, we know approximately how much there is, we know how it's distributed, but we don't know what it is. That's an uncomfortable position for science. Usually, we can study things directly, probe their properties, manipulate them in laboratories. Dark matter refuses these approaches. It sits at the edge of detectability, influencing everything through gravity, but revealing nothing about its fundamental nature. This mystery has led to some alternative theories. Perhaps instead of dark matter, gravity itself works differently on large scales than Einstein's general relativity predicts. Modified gravity theories attempt to reproduce the observations without invoking invisible matter. Some have had limited success explaining galaxy rotation curves or certain aspects of structure formation, but none have successfully explained the full range of observations as well as dark matter does. The Bullet cluster in particular is very difficult to explain without invoking some form of invisible matter. For now, dark matter remains the best explanation we have. Something invisible and massive fills the universe, forming the scaffolding of cosmic structure. It's there in the halos around galaxies, in the filaments of the cosmic web, in the extended atmospheres of galaxy clusters. It outnumbers ordinary matter by about 5 to 1. It was crucial to structure formation in the early universe, clumping first and allowing ordinary matter to follow. And it continues to shape the cosmos today, determining where galaxies form, how they move, when they merge. Living in a universe dominated by dark matter creates an odd situation. Most of what exists, by mass, is invisible to us. We're surrounded by a substance we've never seen and may never directly detect. Right now, dark matter particles, whatever they are passing through your body, through the Earth, through the solar system, completely unnoticed. They're everywhere, constituting the majority of matter in the universe, yet they leave no trace in your immediate experience. That might seem alienating, but it can also be humbling. We've always known that human senses perceive only a narrow slice of reality. We can't see ultraviolet light or infrared. We can't hear ultrasound. We can't detect magnetic fields directly or sense radioactivity. Dark matter is just another reminder that reality extends far beyond what our senses reveal. The universe doesn't arrange itself for our convenience. We have to meet it on its own terms. The spaces between galaxies, then, are filled with dark matter in vast quantities. It's the main ingredient by mass, far outnumbering the scattered atoms of ordinary gas. This invisible ocean determines the structure of everything visible. The cosmic web is really a dark matter web, with galaxies and gas marking where the invisible filaments run. The voids are regions where even dark matter is scarce, though never absent. Every feature of large-scale structure traces back to dark matter's distribution. As you think about this invisible scaffolding, this hidden architecture that pervades space, you might feel a sense of wonder. The universe contains so much more than appears at first glance. The darkness isn't empty. It's full of matter we can't see. Matter that's essential to existence as we know it. Without dark matter's gravity, the first galaxies might never have formed. Stars might not exist. We might not exist. The visible universe depends on the invisible one in ways we're only beginning to understand. Dark matter is patient. It doesn't shine, doesn't demand attention, doesn't announce itself. It simply exists, exerting gravity, shaping space, holding everything together. In that patience, in that quiet presence, lies a lesson about reality. Not everything important is obvious. Not everything powerful is visible. Sometimes the most essential things are the ones you can sense only indirectly, through their effects on everything else. And the spaces between galaxies, filled with this invisible substance, remind us that the universe always contains more than we can see. More structure, more matter, more mystery. If dark matter is the universe's hidden scaffolding, then dark energy is its breath, the force that causes space itself to expand and carries everything apart. It's even more mysterious than dark matter, accounting for roughly 70% of the universe's total energy content, yet remaining completely invisible and undetectable except through its effects on the cosmos's expansion. Dark energy is the force of emptiness, a pressure inherent to space itself that pushes everything away from everything else. The discovery of dark energy came as a shock. In the late 1990s, two teams of astronomers were measuring distances to distant supernovae, trying to determine how fast the universe's expansion was slowing down. Everyone expected gravity to be gradually decelerating expansion, pulling everything back together. But the observations showed the opposite. Distant supernovae were fainter than expected, meaning they were farther away than they should be if expansion were slowing. The universe wasn't just expanding, it was accelerating. This acceleration could only be explained if something was counteracting gravity's attractive pull. Something had to be pushing space apart, and that something had to be spread uniformly throughout the universe, growing stronger as space grew larger. The simplest explanation was that empty space itself had energy, a property Einstein had once included in his equations as the cosmological constant but later abandoned. That vacuum energy, if it existed, would create a kind of repulsive gravity, driving accelerated expansion. The name dark energy was coined to describe this mysterious component, following the naming convention of dark matter. Like dark matter, it doesn't emit or absorb light. Unlike dark matter, it doesn't clump or cluster. It's perfectly uniform, with exactly the same density everywhere. Every cubic meter of space contains the same amount of dark energy, whether that space is inside a galaxy or in the deepest cosmic void. This uniformity makes it fundamentally different from any other known form of energy or matter. Dark energy's effects are negligible on small scales. Within galaxies, within the solar system, even within galaxy clusters, gravity dominates. The local attraction of matter overwhelms dark energy's cosmic push, but on larger scales, across the distances between galaxy clusters, dark energy becomes increasingly important. It drives the expansion of space, causing clusters to recede from each other faster and faster. In the deepest voids, where matter is scarcest, dark energy completely dominates, determining how space evolves there. The physical nature of dark energy remains unknown. The simplest theory identifies it with vacuum energy, the idea that even empty space has a baseline energy density. Quantum mechanics predicts that the vacuum should be full of fleeting particle-antiparticle pairs that appear and vanish too quickly to observe directly. These quantum fluctuations should contribute to the vacuum's energy. The problem is that when you calculate what that energy should be, you get a number about 120 orders of magnitude larger than what observations require. It's the worst theoretical prediction in the history of physics. That enormous discrepancy suggests we don't understand something fundamental about how quantum mechanics and gravity interact. Maybe there's a cancellation mechanism we haven't discovered that reduces the vacuum energy to its observed value. Maybe our understanding of quantum fluctuations in curved spacetime is incomplete. Or maybe vacuum energy isn't the right explanation at all, and dark energy is something else entirely. Alternative theories propose that dark energy is a field, similar to the electromagnetic field, or the field thought to drive cosmic inflation in the early universe. These quintessence models suggest that dark energy could vary in strength over time or space, evolving as the universe ages. If true, dark energy's properties might have been different in the past and could change in the future. Observations so far show no evidence of such variation, but the measurements aren't precise enough to rule it out completely. Some theories question whether dark energy exists at all. Perhaps what we interpret as acceleration is actually a sign that gravity works differently on cosmic scales than Einstein's general relativity predicts. Modified gravity theories attempt to explain the observations without invoking a mysterious vacuum energy. Some have shown promise in specific contexts, but none have successfully explained the full range of cosmological observations as well as dark energy does. For now, dark energy remains the leading explanation. Something fills space uniformly, exerts negative pressure, and drives accelerated expansion. That something makes up about 70% of the universe's energy budget, meaning the majority of what exists is this mysterious cosmic pressure. Dark energy dominates the universe, determining its large-scale dynamics and its ultimate fate, yet we don't know what it is or why it has the precise value it does. The spaces between galaxies are where dark energy matters most. In these vast regions, where matter is sparse, dark energy's uniform pressure becomes the dominant force. It pushes on every point in space equally, causing space to expand uniformly. This expansion doesn't mean galaxies are moving through space. It means space itself is growing, carrying the galaxies along like dots on an inflating balloon. The farther apart two galaxies are, the faster the space between them expands, making them recede from each other ever more quickly. This effect is already significant. Galaxy clusters that aren't gravitationally bound to each other are receding at speeds proportional to their separation. The most distant galaxies we can see are moving away from us faster than light, though they're not moving through space that fast. Space between us and them is expanding so rapidly that the total recession velocity exceeds light speed. This doesn't violate relativity, which only limits motion through space, not the expansion of space itself. As dark energy continues to drive expansion, its effects will grow more pronounced. The space between galaxy clusters will increase until most clusters recede beyond each other's cosmic horizons, the distance beyond which light can never reach us no matter how long we wait. In the far future, observers in a given galaxy will be able to see only their local cluster and perhaps a few nearby ones. Everything else will have disappeared beyond the horizon, its light forever redshifted into undetectability. This future isolation is a consequence of dark energy's dominance. As the universe ages, the matter density decreases as space expands. Dark energy's density remains constant. Eventually, dark energy will completely dominate, with matter's gravitational influence becoming negligible. The cosmic web will dissolve as the filaments connecting clusters stretch beyond their ability to hold together. The universe will consist of isolated island clusters in an ever-expanding sea of space. But that's trillions of years away. For now, dark energy and dark matter coexist in approximate balance at the largest scales, with dark energy just beginning to dominate. This epoch is special. Earlier in the universe's history, matter dominated, and expansion was decelerating. Later, dark energy will completely dominate, and structure formation will cease. We live in a transition period when both components matter, when the universe is structured but also accelerating, when we can still observe the cosmic web before expansion tears it apart. The existence of dark energy raises profound questions. Why does vacuum energy have the specific value it does? Why is it comparable to matter density right now, in this particular cosmic epoch? If it had been much larger, the universe would have expanded too quickly for structures to form. If it had been much smaller, we wouldn't notice it. The fact that it's just right for structure to form but also detectable suggests something special about the current era, though we don't understand what. Some scientists invoke the anthropic principle. Perhaps dark energy varies across different regions of a vast multiverse, and we necessarily find ourselves in a region where it's small enough to allow structure formation, because only in such regions can observers like us exist. This explanation is controversial, seeming to trade one mystery for another, but it illustrates how puzzling dark energy's properties are. Living in a universe dominated by dark energy means living in a universe that will expand forever. There will be no big crunch, no eventual collapse back to a single point. Instead, expansion will continue accelerating, space will grow without limit, and the universe will become ever emptier and colder. The stars will eventually burn out, black holes will evaporate, and only the faintest quantum processes will disturb the darkness. It's a slow fade, rather than a dramatic end. Dark energy teaches us that emptiness isn't passive. Space isn't just a background stage where events unfold. It's an active participant with properties and dynamics of its own. The vacuum has energy and pressure. It can push as well as contain. And on the largest scales, its push determines the cosmos's fate more than anything else. The force of emptiness is the universe's dominant force. As you think about dark energy, about this mysterious pressure filling every corner of space, including the room around you right now, you might feel a strange mix of emotions. Wonder that reality contains such a thing, a force that pervades everything, yet reveals itself only on cosmic scales. Humility that we understand so little about what makes up most of the universe, and perhaps a calm acceptance that the universe is more subtle and strange than our everyday experience suggests. The spaces between galaxies are saturated with dark energy. Every cubic meter, every point in space, carries this pressure that drives expansion. It's the most uniform thing in existence, the same everywhere and everywhen, as far as we can tell, and it's shaping the universe's future in ways we can calculate but not fully comprehend. Dark energy is the force that will eventually isolate every galaxy, dissolving the cosmic web, leaving only darkness between the scattered islands of light that remain. It's patient, inexorable, and utterly mysterious, the universe's dominant component and its deepest puzzle. Light is our primary connection to the universe beyond Earth. Every star we see, every galaxy we photograph, every distant object we study, we know through the light it sends us. But light, travelling through the spaces between galaxies, doesn't arrive unchanged. The vast distances stretch it, thin it, and sometimes scatter it, transforming the message it carries. Understanding what happens to light crossing the intergalactic medium is essential to understanding what we see when we look into deep space. When light leaves a distant galaxy, it begins a journey that might last billions of years. During that journey, it travels through expanding space. This expansion doesn't just increase the distance light has to cover, it actually stretches the light itself, elongating its wavelength. A photon that began as visible light might arrive as infrared. One that started as ultraviolet might end up visible. This stretching, called redshift because it shifts light toward the red end of the spectrum, is one of astronomy's most important tools for measuring cosmic distances. The more distant the source, the longer the light travels, and the more it's redshifted. Light from the nearest large galaxy, Andromeda, is barely shifted at all because it travelled through relatively little expansion. Light from galaxies a billion light-years away shows moderate redshift. Light from the most distant galaxies we can observe, emitted when the universe was young, is redshifted so much that what was once ultraviolet has become infrared, requiring special telescopes to detect it. This redshift isn't caused by the galaxy moving through space, though that can add additional shift. It's caused by space itself expanding during the light's journey. The space the light travels through grows, and the light grows with it. By the time the photon reaches us, it's been stretched thin by billions of years of expansion, carrying less energy than when it began. In that sense, light lost to distance isn't just dimmed by spreading out, it's fundamentally altered, changed by the journey itself. But redshift is just one way the intergalactic medium affects light. The scattered atoms of gas between galaxies, though sparse, can absorb specific wavelengths. When light from a distant quasar passes through a cloud of hydrogen, the hydrogen atoms absorb light at particular frequencies, leaving dark lines in the quasar's spectrum. These absorption lines appear not just once but many times, each set corresponding to a different cloud of gas at a different distance. Astronomers call this pattern the Lyman alpha forest, a series of absorption lines that looks like a barcode marking every hydrogen cloud the light encountered. By studying this forest, scientists can map the distribution of gas between us and the quasar, measuring the density and temperature of the intergalactic medium at different times in cosmic history. The light's journey becomes a record of everything it passed through, a cosmic travelogue written in absorption patterns. Sometimes the intergalactic medium contains heavier elements, not just hydrogen and helium. These elements, forged in stars and scattered into space by supernovae, leave their own distinctive absorption patterns. Carbon, oxygen, silicon, iron, each has a unique spectral signature. Finding these elements in the intergalactic medium tells us that galaxies have been polluting space with heavy elements for billions of years, enriching what was once pristine primordial gas. Light can also be scattered by the intergalactic medium, though this effect is usually subtle. When photons interact with free electrons in hot gas, they can be deflected slightly, changing direction or energy. This Compton scattering is most important in galaxy clusters, where hot gas is relatively dense. For light travelling through the more diffuse gas between clusters, scattering is negligible. Most photons pass through unimpeded, travelling in straight lines from source to observer. Gravitational effects also alter light's path. When light passes near a massive galaxy or cluster, gravity bends its trajectory, an effect called gravitational lensing. From our perspective, this can magnify distant galaxies, brighten them, or create multiple images of the same source. Lensing reveals where mass is concentrated, including dark matter that doesn't emit light. The intergalactic medium's dark matter, distributed in halos and filaments, creates a subtle background of weak lensing that affects nearly all distant light. As light travels, it also dims simply by spreading out. Imagine a sphere expanding around a light source. The same amount of light energy has to cover the sphere's entire surface, which grows as the square of distance. By the time light from a distant galaxy reaches us, it's spread over an enormous area, making the galaxy appear faint even if it's intrinsically bright. This geometric dimming combines with redshifts energy loss to make distant galaxies incredibly dim. The faintest galaxies we can detect required instruments to gather light for weeks or months, collecting photons one by one from sources billions of light years away. Each photon is ancient, having travelled for most of the universe's history. Some began their journey before Earth existed. They crossed the intergalactic medium, passing through gas clouds and gravitational fields, surviving everything space could throw at them, only to end their journey in a telescope's detector, contributing one tiny piece to humanity's understanding of the cosmos. There's something poignant about those photons. They've travelled unimaginable distances, witnessed cosmic history, crossed voids and filaments, and arrived here to tell us about a galaxy as it was billions of years ago. That galaxy has changed since the light left. It might have merged with others, exhausted its gas, or had its star formation quenched by interactions with neighbours. The light shows us not what the galaxy is, but what it was. We're looking into the past, seeing history preserved in photons. The farthest light we can detect comes from the cosmic microwave background, the afterglow of the Big Bang itself. This light was emitted when the universe was only 380,000 years old, long before the first stars formed. Since then, it's been travelling through expanding space, redshifted from visible and ultraviolet wavelengths into microwaves. That light has passed through the entire history of structure formation, through the cosmic dark ages before stars, through the epoch of reionization when the first galaxies formed, through billions of years of cosmic evolution. The cosmic microwave background fills the entire sky, a nearly uniform glow in every direction. It's the oldest light we can observe, and it marks the edge of the observable universe. Before that light was emitted, the universe was opaque, too hot and dense for light to travel freely. The microwave background is our horizon, the farthest back we can see. Beyond it lies the universe's first few 100,000 years, forever hidden from direct observation. But even this ancient light carries information about what lies between us and its source. The microwave photons pass through galaxy clusters on their way to us, interacting slightly with the hot gas there. This interaction, the Sunyaev-Zeldovich effect, creates slight distortions in the background's temperature. By mapping these distortions, astronomers can find galaxy clusters and study the intergalactic medium's distribution even in distant regions where other observations are difficult. Light traveling through the intergalactic medium is also affected by the universe's transparency, or lack thereof. In the early universe, before the first stars formed, space was filled with neutral hydrogen that absorbed ultraviolet light efficiently. The universe was dark, opaque to certain wavelengths. Then the first stars ignited, flooding space with radiation that ionized the hydrogen, making it transparent again. This reionization changed the universe from opaque to transparent over a period of a few 100 million years. We can observe this transition by looking at distant quasars. Light from quasars beyond a certain distance shows strong absorption from neutral hydrogen, indicating it's passing through the pre-reionization universe. Light from slightly closer quasars shows less absorption, indicating the universe has become more transparent. By studying how absorption changes with distance, astronomers can map when and how reionization occurred, learning about the first generation of stars and galaxies. As expansion continues and dark energy drives galaxies farther apart, more light will be lost to distance. Galaxies that we can see now will eventually recede beyond the cosmic horizon. Their light redshifted so much that it becomes undetectable. The universe will appear emptier from any given vantage point, not because galaxies have disappeared, but because their light can no longer reach us. The spaces between will grow so large that light, even travelling at its ultimate speed, can't keep up with expansion. This future light loss means that future observers, if any exist, will have access to less information about the universe than we do now. They'll live in a cosmos that seems smaller, simpler, more isolated. They won't be able to see the cosmic microwave background as we do. They won't be able to measure the expansion rate from distant supernovae. They might not even realize the universe is expanding if all observable galaxies are gravitationally bound to each other locally. We live in a privileged epoch for cosmology, when the universe reveals its full structure and history. But for now, light still reaches us from distant sources, carrying information about what lies between galaxies. Every photon is a messenger, telling us about the gas it passed through, the gravity it felt, the expansion it experienced. When we decode those messages, we learn about the intergalactic medium's properties, about dark matter's distribution, about dark energy's effects. Light, lost to distance, isn't really lost. It's transformed, enriched with information about the journey, arriving changed but bearing witness to everything it encountered along the way. Between the galaxies, scattered so thinly they're almost not there at all, drift atoms of hydrogen and helium, the universe's most abundant elements. They form what astronomers call the intergalactic medium, a vast diffuse gas that fills the spaces we think of as empty. To call it a gas feels almost misleading. The density is so low that on Earth we'd call it the best vacuum ever created. Yet, across cosmic scales, those scattered atoms add up to something significant, something that matters. For every cubic meter of intergalactic space, you might find one or two atoms, sometimes fewer. In the voids, the density drops even lower, but multiply that across the billions upon billions of cubic meters between galaxies, and you accumulate substantial mass. In fact, the intergalactic medium contains most of the ordinary matter in the universe, more than exists in all the stars and planets combined. What seems like nothing is, collectively, most of everything. These atoms aren't still. They're moving, drifting through space at speeds determined by their temperature. In some regions, where gravity has pulled gas into filaments, or where radiation from nearby galaxies has heated it, the atoms move rapidly, with temperatures reaching millions of degrees. In the deepest voids, far from any energy source, they drift slowly through a near-perfect cold, just degrees above absolute zero. The composition of the intergalactic medium tells a story of cosmic history. Most of it is hydrogen, the simplest element, formed in the first few minutes after the Big Bang, when the universe was hot enough for nuclear fusion. About a quarter is helium, also forged in those earliest moments. But mixed throughout, in trace amounts, are heavier elements: carbon, oxygen, nitrogen, iron. These elements didn't exist in the early universe. They were created later, inside stars, and scattered into space when those stars died. Finding heavy elements in the intergalactic medium reveals that galaxies aren't closed systems. They exchange matter with their surroundings. When massive stars explode as supernovae, they blast enriched material into space. When supermassive black holes at galaxy centers launch jets, they push gas outward. Over billions of years, this process has gradually polluted the intergalactic medium, enriching what was once pristine primordial gas with the products of stellar nucleosynthesis. The intergalactic medium isn't uniformly distributed. It follows the cosmic web structure, denser along filaments, thinner in voids. Where dark matter forms invisible threads connecting galaxy clusters, the gas accumulates, flowing along gravitational channels like water through invisible pipes. These flows are slow by human standards but significant over cosmic time. Gas moves from voids toward filaments, from filaments toward galaxies, in a continuous circulation that feeds star formation and galaxy growth. This circulation, the cosmic baryon cycle, is essential to understanding how galaxies evolve. Galaxies need gas to form new stars, but star formation is inefficient, and without fresh supplies, galaxies would exhaust their gas relatively quickly. The intergalactic medium serves as a reservoir, continuously replenishing galaxies with new material. Gas flows in, forms stars, and is sometimes expelled back into intergalactic space by supernovae or black hole activity. Then it cools, recondenses, and flows back in again. The cycle continues over billions of years. Observing the intergalactic medium directly is challenging because it's so diffuse. It doesn't emit much light on its own. The atoms are too spread out, colliding too rarely to produce significant radiation. Instead, astronomers detect it indirectly, using light from distant quasars as backlighting. As that light passes through the intergalactic medium, gas clouds absorb specific wavelengths, leaving fingerprints in the quasar's spectrum. Each absorption line represents a cloud at a particular distance, allowing scientists to map the medium's distribution across billions of light years. In the voids, it's cold, perhaps 10,000 degrees or less. Along filaments, it warms to hundreds of thousands of degrees as gravity compresses it. Near galaxy clusters, where filaments converge and matter accumulates, it can reach tens of millions of degrees. This hot gas glows faintly in X-rays, detectable by space-based telescopes sensitive to those wavelengths. The glow is faint, requiring long observations to detect, but it reveals the medium's structure and composition. One of the medium's most important phases is what scientists call the warm-hot intergalactic medium, or WIM. This gas, heated to temperatures between 100,000 and 10 million degrees, is thought to contain much of the universe's ordinary matter. It's too hot to absorb visible light efficiently, but too cool to emit strong X-rays, making it difficult to observe directly. Its existence was predicted theoretically and confirmed only gradually through careful observations of absorption lines in ultraviolet and X-ray light from distant sources. The intergalactic medium also contains free electrons, stripped from atoms by energetic radiation. These electrons can scatter light through a process called Compton scattering. When photons from the cosmic microwave background pass through hot gas containing free electrons, they can gain energy, shifting to slightly shorter wavelengths. This effect, the Sunyaev-Zeldovich effect, creates subtle distortions in the microwave background's temperature map, revealing where hot gas lies even if we can't see it directly. Over time, the intergalactic medium has evolved. In the early universe, it was denser and cooler, nearly uniform in distribution. As structures formed and galaxies grew, the medium became more structured, following the cosmic web's filaments and avoiding the voids. It also became more enriched. As generations of stars added heavy elements, the medium we observe today is a palimpsest, carrying signatures of billions of years of cosmic evolution, of countless stellar deaths, of gas flows and galactic feedback. The medium's future evolution depends on dark energy and expansion. As the universe grows, the density of the intergalactic medium decreases. The atoms drift farther apart, the temperature drops, the flows along, filaments weaken. Eventually, if expansion continues accelerating, the medium will become so diffuse that interactions between atoms become vanishingly rare. Each atom will drift in isolation, moving away from every other atom, in a universe so empty that even this nearly empty medium seems crowded by comparison. But that's trillions of years away. For now, the intergalactic medium remains active, dynamic, part of the ongoing story of cosmic evolution. It feeds galaxies with fresh gas. It transports energy and matter across vast distances. It connects structures that seem isolated, creating a continuous ocean of matter that extends throughout space. When we look at the darkness between galaxies, this is part of what fills it. Not emptiness, but the thinnest possible sea. An ocean of atoms spread across the cosmos. There's something beautiful about the intergalactic medium's subtlety. It doesn't announce itself. It doesn't glow brightly or create obvious structures. It simply exists, nearly invisible, barely there, yet essential to everything. Without it, galaxies would have no fuel for new stars. The cosmic web would lack its connecting tissue. The universe would be fundamentally different, a collection of isolated islands rather than a connected whole. As you think about this nearly invisible sea, you might notice the parallel to other subtle presences in the world. The air around you is mostly invisible, yet essential. The electromagnetic fields that allow your devices to function can't be seen directly. Even your own thoughts, the very thing experiencing this moment, have no visible form. The intergalactic medium is like that, present and important despite its invisibility, shaping the cosmos through its quiet persistence. So when astronomers talk about what lies between galaxies, the intergalactic medium is part of the answer. Not the whole answer, but an essential piece. A sea of atoms so thin it barely qualifies as matter by Earth standards, yet so vast, so connected that it contains most of the universe's ordinary substance. The medium isn't nothing. It's the whisper of matter, the faintest presence that fills the cosmic darkness. linking everything together in ways that only patient observation reveals. The spaces between galaxies aren't still. Even where matter is sparse and galaxies rare, particles race through the darkness at nearly the speed of light. These are the cosmic rays and neutrinos, invisible travelers that cross the intergalactic medium continuously, silently, carrying energy and information from some of the universe's most violent events. They pass through space, through planets, through you, leaving almost no trace but connecting everything through their ceaseless motion. Cosmic rays aren't rays at all. They're particles, mostly protons, the nuclei of hydrogen atoms, accelerated to tremendous energies by cosmic processes we're only beginning to understand. Supernova explosions can accelerate particles through their expanding shock waves. The jets from supermassive black holes can boost particles to energies millions of times higher than anything achievable in human-made accelerators. Exactly how these processes work remains mysterious, but the results are clear. Space is filled with high-energy particles racing in every direction. Most cosmic rays we detect come from within our own galaxy, accelerated by nearby supernovae and propagating through the Milky Way's magnetic fields. But some have much higher energies, too high to come from any known galactic source. These ultra-high energy cosmic rays must have originated elsewhere, accelerated by processes in other galaxies, or perhaps in the intergalactic medium itself. They've travelled across millions or billions of light years to reach us, their paths bent and scrambled by magnetic fields until their origins are nearly impossible to trace. When a cosmic ray particle strikes Earth's atmosphere, it triggers a cascade of secondary particles, a shower that spreads through the air like an invisible avalanche. Detectors on the ground can measure this shower, reconstructing the energy and direction of the original particle. The highest energy cosmic rays carry as much kinetic energy as a well-thrown baseball, all concentrated in a single atomic nucleus. That's an almost incomprehensible amount of energy for something so small. In the intergalactic medium, cosmic rays travel vast distances with little to slow them. The density is so low that collisions with atoms are rare. Magnetic fields can deflect their paths but don't drain their energy significantly. A cosmic ray accelerated in a distant galaxy might wander through intergalactic space for millions of years before happening to encounter Earth. Its journey is random, determined by every magnetic field it passes through, every slight gravitational tug it feels. These particles help maintain the intergalactic medium's ionization. Even in regions far from any galaxy, where starlight is, faint, cosmic rays passing through can occasionally knock electrons off atoms, keeping some fraction of the gas ionized. This ionization affects how the gas cools and how it responds to gravity. Cosmic rays, despite being incredibly rare compared to ordinary atoms, play a subtle but persistent role in the medium's physics. Then there are neutrinos, particles even more elusive than cosmic rays. Neutrinos barely interact with anything. They're produced in enormous numbers by stars, by supernovae, by black holes, even by the Big Bang itself, but they pass through matter as if it weren't there. A neutrino can travel through the entire Earth without noticing. It can cross the intergalactic medium for billions of years without once colliding with an atom. For neutrinos, the universe is essentially transparent. Detecting neutrinos requires enormous detectors and tremendous patience. Scientists build massive tanks of water or use entire cubic kilometers of Antarctic ice as detection medium. When a rare neutrino does interact with an atom, it produces a faint flash of light. By surrounding the detector with sensitive instruments, physicists can catch those flashes and reconstruct where the neutrino came from and how much energy it carried. Even then, only a tiny fraction of passing neutrinos are detected. Most escape unnoticed. Despite their elusiveness, neutrinos carry valuable information. Unlike light, which can be absorbed or scattered, neutrinos travel in straight lines from their source. Detecting a neutrino from a distant galaxy tells you something energetic is happening there, something that produced high-energy particles. Over the past decade, astronomers have begun using neutrinos as a new way to observe the universe, complementing traditional telescopes that detect light. The intergalactic medium is filled with neutrinos from countless sources. Some were produced in the Big Bang itself, cooled by expansion to nearly zero energy, but still present in vast numbers. Others come from stars throughout the universe, streaming out from nuclear reactions in stellar cores. Still others are produced by violent events, by supernova explosions, by matter falling into black holes, by cosmic ray collisions with gas or starlight. All of them travel endlessly through space, an invisible rain of particles that nothing can stop. In a sense, cosmic rays and neutrinos represent the universe's background noise, its continuous activity that exists even in the seemingly empty spaces between galaxies. They remind us that the cosmos is never truly still. Energy is always being transported from place to place. Particles are always moving. Even in the deepest voids, this microscopic traffic continues, invisible but unceasing. For humans, the practical effects are negligible. Cosmic rays occasionally flip bits in computer memory or contribute to background radiation exposure, but the effect is tiny compared to radiation from natural sources on Earth. Neutrinos pass through us by the trillions every second without ever interacting, harmless and unnoticed. We're bathed in this cosmic particle flux constantly, completely unaware of it without specialized instruments to detect it. But on cosmic scales, these particles matter. They transport energy across vast distances. They provide information about distant events that might be obscured by dust or hidden from view. They connect different regions of space through their motion, linking sources and destinations that might seem isolated. In that way, cosmic rays and neutrinos are part of the continuous communication network that threads through the universe, carrying messages in a language we're only beginning to learn to read. The highest energy cosmic rays remain mysterious. Where do they come from? What accelerates them to such extreme energies? The particles themselves don't reveal their origins because magnetic fields scramble their paths. Theories suggest they might be accelerated by supermassive black holes, by the jets from active galaxies, or by exotic processes in the intergalactic medium itself. Each new detection adds data, but the full picture remains unclear. The universe's most energetic particles are also its most enigmatic. Thinking about these invisible travelers, racing through space at nearly the speed of light, you might feel a sense of the universe's dynamism. Nothing is static. Everything moves. Even in the emptiest regions, particles are flowing, carrying energy, connecting distant places through their ceaseless motion. The darkness between galaxies isn't passive or dead. It's alive with traffic, with particles crossing vast distances, with energy being exchanged continuously across cosmic scales. And perhaps there's something comforting in that. You're not separate from this cosmic activity. Right now, neutrinos from the sun are streaming through your body. Cosmic rays from distant galaxies are striking the atmosphere above you. You're part of the same flow of particles and energy that fills the intergalactic medium. The universe's invisible traffic passes through you every moment, connecting you to everything else. You're not an isolated observer, but a participant, embedded in the same field of motion and energy that extends throughout space. There's another kind of signal that passes through the spaces between galaxies, one that doesn't involve particles or light at all. These are gravitational waves, ripples in the fabric of space-time itself, produced by massive objects accelerating violently. When two black holes spiral together and merge, when neutron stars collide, when supermassive black holes at galaxy centers dance around each other, they send gravitational waves racing outward through the universe at the speed of light. Gravitational waves are unlike anything else. They're not electromagnetic radiation. They're not particles. They're distortions in space-time's geometry, oscillations in the distances between points. When a gravitational wave passes through you, it stretches space in one direction and compresses it in another, alternating rhythmically. The effect is incredibly tiny, changing distances by less than the width of an atomic nucleus, even for the strongest waves we can detect. Yet it's real, measurable, and now observed regularly by gravitational wave observatories around the world. The first direct detection of gravitational waves came in 2015, exactly 100 years after Einstein predicted their existence. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected a signal lasting less than a second. The unmistakable signature of two black holes, each about 30 times the mass of the Sun, spiraling together and merging more than 1 billion light-years away. The detection confirmed a fundamental prediction of general relativity and opened a completely new way to observe the universe. Since then, dozens of gravitational wave events have been detected. Most are black hole mergers, though some are neutron star collisions. Each detection reveals information about the merging objects, their masses, spins, distances, and because gravitational waves travel through space-time itself, they carry pristine information, unaffected by dust or gas that might obscure light from the same event. They pass through the intergalactic medium without scattering or absorption, arriving unchanged from their source. The intergalactic medium is essentially transparent to gravitational waves. While light can be absorbed by gas, while cosmic rays can be deflected by magnetic fields, gravitational waves simply pass through everything as if it weren't there. They're the purest messengers, carrying information across billions of light-years without alteration. When we detect a gravitational wave, we're sensing space-time's response to an event that happened long ago and far away, preserved perfectly in the geometry of the waves themselves. Gravitational waves also fill space as a continuous background. Every pair of orbiting objects, from binary stars to merging galaxies, produces gravitational radiation. Most individual sources are too weak to detect, but collectively they create a stochastic background, a kind of gravitational noise that permeates the universe. Detecting this background is one of the goals of pulsar timing arrays, which use pulsars as natural gravitational wave detectors, sensitive to lower frequencies than ground-based instruments can measure. Recent observations suggest we're beginning to detect this background. By monitoring the timing of pulses from multiple pulsars scattered across the sky, astronomers have found correlated variations that match what gravitational waves would produce. If confirmed, this would be the first evidence of the universe's gravitational wave background, a hum of space-time oscillations from countless sources throughout cosmic history. In the intergalactic medium, these waves propagate freely. They carry energy away from their sources, gradually draining the orbital energy of binary systems and causing them to spiral inward. Over millions or billions of years, gravitational radiation is what ultimately causes binary black holes to merge, binary neutron stars to collide, and binary galaxies to come together. The waves don't just tell us about these events. They're part of the physical process that makes them happen. There's something profound about gravitational waves as a concept. They reveal that space-time isn't a fixed stage, but a dynamic entity that can vibrate, oscillate and carry information. The spaces between galaxies aren't just geometric extension, they're a physical medium with properties and behaviors of its own. Gravity isn't just a force pulling objects together, it's the curvature of space-time, and that curvature can ripple outward like waves on a pond. When two supermassive black holes at the centers of merging galaxies eventually spiral together, they'll produce gravitational waves of such strength that they'll be detectable across most of the observable universe. These events are rare, but when they occur, they release more energy in gravitational waves than all the stars in all the galaxies emit as light during the same time. That energy propagates outward through the intergalactic medium as space-time oscillations, stretching and compressing everything slightly as it passes. Future space-based gravitational wave detectors will observe lower frequency waves than current ground-based instruments can detect. They'll be sensitive to mergers of supermassive black holes, to extreme mass ratio in spirals where stellar mass objects fall into supermassive black holes, to signals from the early universe that might reveal physics beyond our current understanding. These observations will tell us more about what happens in the spaces between galaxies, how structures grow and merge, how black holes evolve. The gravitational wave background also carries information about the universe's structure. Waves passing through regions of varying density experience subtle effects, slight delays or deflections caused by the gravitational fields they traverse. By studying how waves from distant sources are affected by intervening matter, astronomers can learn about the distribution of mass throughout the universe, including dark matter that doesn't reveal itself in any other way. In a sense, gravitational waves provide a way to hear the universe. When scientists convert gravitational wave signals into sound frequencies, the result is a chirp, a rising tone as the orbiting objects spiral faster and faster before merging. It's not a real sound. There's no medium for sound in space, but it represents the rhythm of the event, the pattern of space-time oscillations. Listening to these converted signals gives a visceral sense of cosmic events that graphs and numbers can't quite capture. The universe, then, is filled with gravitational echoes, memories of violent events that happened millions or billions of years ago. Those echoes travel endlessly through space, passing through galaxies and intergalactic medium alike, carrying information about the objects that created them. Some will eventually reach us, briefly disturbing our detectors before continuing outward. Others will travel forever, oscillations in space-time that will persist long after their sources have faded into darkness. There's a certain poetry to gravitational waves. They're space-time talking to itself, ripples in the very fabric of existence. They connect everything, not through particles or fields, but through geometry. Every massive object that accelerates creates them, from orbiting stars to merging galaxies. They fill the universe with motion at the deepest level, oscillations in the structure of space and time itself. And the spaces between galaxies, far from being static, are alive with these waves, these gravitational echoes that testify to the universe's dynamic nature. As you lie there, thinking about gravitational waves passing through the room around you, through your body, through the earth, perhaps you can imagine the faint stretch and compression they create. It's far too small to feel, but it's there, a cosmic signal threading through everything. The universe is vibrating, gently and continuously, responding to events across vast distances and times. And you're part of that vibration, embedded in the same space-time that carries these waves, connected through geometry to everything else that exists. Not all the light between galaxies comes from distant sources. Some comes from stars that don't belong to any galaxy at all, orphans kicked out of their homes by gravitational interactions. now drifting alone through the intergalactic medium. These stars are rare and faint, almost impossible to see individually, but collectively they produce a diffuse glow that fills the spaces between galaxies and clusters. It's called intracluster light, and it tells a story of galactic violence and cosmic rearrangement. When galaxies pass close to each other, their mutual gravity creates tidal forces that can tear stars from their outer regions. Some of those stars are flung outward at high speed, escaping the galaxy entirely and becoming intracluster stars. Others are drawn out in long streams that mark the path of the encounter. Over billions of years, as galaxies within a cluster collide and merge repeatedly, they shed stars into the intergalactic space, gradually building up a population of orphans. These orphan stars are challenging to observe because they're so dispersed. Unlike stars in a galaxy, which cluster together and create bright regions we can see from great distances, intracluster stars are spread thinly across millions of light years. Their collective light is faint, often less than 1% of the cluster's total light. Detecting it requires extremely sensitive instruments and sophisticated analysis to separate it from the much brighter galaxies in the foreground. But when astronomers do detect intracluster light, they find it surprisingly common. Most large galaxy clusters show evidence of it, a diffuse glow that extends between galaxies like a fog. The color of this light reveals that it comes from stars similar to those in galaxies, confirming that these are indeed orphaned stars rather than some other phenomenon. The distribution tells us about how often galaxies interact, how violently, and how much mass they've exchanged over cosmic time. Some of the most striking images of intracluster light come from deep observations of nearby clusters. These images, taken with exquisite care to remove light from individual galaxies and the Earth's atmosphere, reveal faint streams and bridges connecting galaxies, tidal tails marking past encounters, and a general haze surrounding the cluster's center. It's like seeing the bones beneath the cluster's skin, the structure hidden by the bright light of galaxies themselves. The orphan stars aren't just old remnants. Some are young, pulled from galaxies that are still actively forming stars. When gas-rich galaxies interact, they can lose not just stars but also clouds of gas, which then float in the intergalactic medium. Under the right conditions, that gas can cool and condense, forming new stars directly in intergalactic space. These stars are truly homeless, born in the void, never belonging to any galaxy. Imagine being on a planet orbiting one of these orphan stars. Your night sky would be profoundly different from Earth's. There would be no Milky Way, no band of diffuse light from a galaxy's disk surrounding you. Instead, you'd see galaxies scattered across the sky, each one a distinct fuzzy patch, none particularly close. The nearest might be a few million light years away. The sky would be darker than anything visible from Earth, filled with distant islands of light but lacking the nearby stars that create our constellations. Yet despite their isolation, orphan stars aren't completely alone. They orbit the cluster's center, held by the combined gravity of all the galaxies and dark matter there. They're part of the cluster's structure, just not part of any individual galaxy. In some ways, they represent the cluster's true stellar population, stars that belong to the cluster as a whole rather than to any single member. They blur the boundary between galaxy and intergalactic medium, showing that the distinction isn't always sharp. The existence of orphan stars also tells us about galaxy evolution. The fact that so many stars have been stripped from galaxies means that galaxies aren't permanent structures. They change over time, losing matter to their surroundings, accreting matter from other galaxies, gradually transforming through countless interactions. The orphan stars, are the evidence of this ongoing transformation. Fossils of past encounters preserved in the darkness between galaxies. Some scientists study intracluster light to learn about dark matter's distribution. Because orphan stars orbit the cluster just like galaxies do, their distribution and motion reflect the underlying dark matter potential. By mapping where the intracluster light is brightest, astronomers can infer where dark matter is most concentrated, adding to the evidence from other techniques like gravitational lensing. The ghost light becomes a tracer of invisible mass. The future of these orphan stars is tied to their cluster's fate. As clusters evolve, galaxies within them continue to interact. More stars will be stripped, adding to the intracluster population. Eventually, in the far future, the galaxies may merge into a single giant elliptical galaxy, incorporating many of the orphan stars. Or, if dark energy continues to dominate, expansion might eventually overcome the cluster's gravity, dispersing its members and leaving the orphan stars truly alone in an ever-expanding void. There's something melancholic but also beautiful about these orphan stars. They're wanderers, cast out from their homes, drifting through darkness, yet they continue to shine, perhaps hosting planets, perhaps surrounded by their own small systems. They're not destroyed by their isolation. They simply continue existing, alone but not diminished, contributing their faint light to the intergalactic medium. When you think about the spaces between galaxies, these orphan stars are part of what fills them, not just gas and dark matter and energy, but actual stars, suns like our own, separated from their galaxies but still shining. They're reminders that the intergalactic medium isn't completely empty, that even in the darkness there are points of light, however faint, testifying to the complex history of cosmic structure formation. The ghost lights of orphan stars show that boundaries in the universe are porous. Galaxies aren't sealed containers. They exchange matter with their surroundings. Stars can cross from one galaxy to another, or escape galaxies entirely. The intergalactic medium receives contributions from galaxies, enriching it, lighting it faintly, connecting everything through the slow exchange of matter over billions of years. Nothing is truly isolated. Everything influences everything else, however subtly. At the densest points in the universe, where gravity becomes so strong that even light cannot escape, lie black holes. These aren't empty voids, despite the name. They're regions where space-time is curved so extremely that it forms a kind of trap, a one-way surface called an event horizon beyond which nothing can return. Black holes exist everywhere, from stellar mass objects formed by collapsing stars to the supermassive giants at galaxy centers, but their influence extends far into the intergalactic medium, shaping how gas flows and connecting distant regions through their gravity. The largest black holes, millions or billions of times more massive than the Sun, sit at the centers of most galaxies. They're not consuming their galaxies, despite science fiction portrayals. Most of the time, they're relatively quiet, accreting matter slowly if at all. But occasionally, when gas falls toward them, they can become extraordinarily bright, outshining all the stars in their host galaxy combined. These active galactic nuclei, or AGN, send radiation and jets of particles streaming into the intergalactic medium, heating gas, preventing it from cooling and forming new stars, dramatically affecting their environments. The jets from supermassive black holes can extend for millions of light years, crossing the intergalactic medium and depositing energy far from their source. These jets are among the most powerful phenomena in the universe, powered by matter falling into the black hole and accelerated to nearly the speed of light by magnetic fields. Where the jets terminate, they create enormous lobes of hot gas and energetic particles, visible in radio wavelengths long after the black hole activity has subsided. These jets influence the intergalactic medium profoundly. They heat gas that might otherwise have cooled and fallen into galaxies to form stars. They stir the gas, creating turbulence that prevents simple flows along the cosmic web's filaments. They inject heavy elements synthesized in stars and processed in the accretion disk. In galaxy clusters, black hole jets help maintain the temperature of the hot intracluster gas, balancing cooling that would otherwise allow all the gas to collapse into galaxies. Without this feedback, clusters would look very different. But black holes are also sources of deeper mystery, especially regarding what happens at their centers and whether they might connect different regions of space-time. General relativity's equations, when applied to black holes, suggest strange possibilities. The mathematics allows for solutions where a black hole's center might connect to another region of space, a shortcut through space-time called a wormhole or Einstein-Rosen bridge. These bridges, if they exist, would connect distant parts of the universe or even different universes entirely. The idea is speculative, unsupported by any direct evidence, but it's permitted by the equations. The challenge is that such bridges, even if they formed, would be unstable. They'd collapse too quickly for anything to traverse them. Keeping a wormhole open would require exotic matter with negative energy density, something we've never observed and that might not exist. Still, the mathematics is intriguing. It suggests that black holes might be more than endpoints where matter disappears forever. They might be transitions, places where space-time connects to somewhere else. In some theoretical models, every black hole could give birth to a new universe on the other side, creating a multiverse of connected cosmos, each seeded by black holes in its parent. It's wildly speculative, perhaps impossible, but it illustrates how much we don't know about what black holes really are at their deepest level. Another mystery involves information. When something falls into a black hole, what happens to the information about its quantum state? Does it vanish, violating quantum mechanics' principle that information is conserved? Or is it somehow encoded in the black hole's surface, preserved in ways we don't yet understand? This black hole information paradox has puzzled physicists for decades, suggesting that our understanding of how quantum mechanics and gravity interact is incomplete. One proposed resolution involves Hawking radiation, a quantum effect that allows black holes to emit particles very slowly, gradually evaporating over immense timescales. If this radiation carries information about what fell in, encoded in subtle correlations between emitted particles, then information isn't lost. But the details of how this encoding works remain unclear, touching on the deepest questions about quantum gravity. Black holes in the intergalactic medium exist primarily at galaxy centers, but stellar mass black holes might also wander through intergalactic space, kicked out of their galaxies by gravitational interactions just like orphan stars. These objects would be essentially invisible, too small to accrete much matter, producing no light or other radiation. Yet they'd still exert gravity, still curve space-time around them, still represent regions where the universe's normal rules break down. The connection between black holes and the spaces between galaxies is thus complex. Black holes affect the intergalactic medium through their jets and radiation. They help regulate galaxy growth by heating gas and preventing excessive star formation. They're laboratories for extreme physics, places where gravity is so strong that classical notions of space and time cease to apply. And they might, speculatively, be bridges connecting different regions of the cosmos, though this remains unproven. Thinking about black holes, about these regions where space-time curves so sharply that it traps light itself, evokes a particular kind of awe, They're the universe's most extreme structures, places where physics reaches limits and perhaps breaks down entirely. We can observe their effects on surroundings, see how gas spirals inward and jets shoot outward, but the interior remains hidden behind the event horizon, forever sealed from direct observation. That unknowability is humbling. There are limits to what we can measure, places we can't see into, even in principle. Black holes remind us that the universe contains genuine mysteries, questions we might never fully answer. And yet, they're also natural consequences of the laws of physics, inevitable outcomes when enough mass concentrates in a small region. The strangest objects in existence emerge from the same equations that describe falling apples and orbiting planets. In the spaces between galaxies, black holes matter. They shape the intergalactic medium's evolution. They affect when and where new stars form. They generate the jets that stretch across cosmic voids. And they embody, in their very existence, the universe's capacity for extremes, for pushing physical laws to their breaking points. Whether or not they form bridges to elsewhere, they're already bridges of a kind, connections between the ordinary and the extraordinary, between the understood and the mysterious, between the visible universe and the hidden physics that underlies everything. Black holes stand at the boundary of knowledge, marking how far understanding has reached and how much farther it has yet to go. In the spaces between galaxies, there is no sound, not the quiet of a library or the hush of snowfall, but absolute silence. Sound requires a medium, molecules of air or water to vibrate and propagate pressure waves. In the near vacuum of intergalactic space, with only 1 or 2 atoms per cubic meter, there's nothing to carry. Sound. Even the most violent cosmic events, exploding stars and colliding galaxies, unfold in perfect soundlessness. The universe speaks, but not in voices. This silence is profound and inescapable. If you could somehow float in the intergalactic medium, surrounded by galaxies millions of light years away, you would hear nothing. Not a whisper, not a hum, not the faintest vibration. Your ears, evolved to sense pressure waves in dense air, would find nothing to detect. The cosmos would reveal itself only to your eyes, and even then, only faintly, in scattered distant lights too dim to cast shadows. Yet the universe isn't truly silent. It vibrates, oscillates, and resonates in ways that don't produce sound, but that carry information nonetheless. The cosmic microwave background, that faint glow from the early universe, represents the fossil record of ancient sound waves. Before atoms formed, when the universe was a hot plasma, pressure waves travelled through it, compressions, and rarefactions that were, in a sense, sound. Those waves are frozen now, in the temperature pattern of the microwave background, a snapshot of the universe's last sound before it fell silent. Scientists have converted those patterns into audible tones, translating the frequency of the early universe's vibrations into sound we can hear. The result is a deep, complex tone, like a chord played on an impossibly large instrument. It's not a real sound, of course. It's a representation, a way of making the universe's ancient rhythms accessible to human senses. But it captures something essential about the cosmos's early state, when it rang with vibrations that would eventually seed galaxy formation. Gravitational waves, too, have frequencies that can be converted into sound. When LIGO detects the merger of 2 black holes, scientists translate the space-time oscillations into audio frequencies, producing chirps and whoops that represent the rhythm of the collision. Again, these aren't real sounds. Space doesn't vibrate the way air does, but the translation helps us grasp the event's dynamics. The way the black holes spiraled faster and faster before merging in a final burst of gravitational radiation. The silence of the intergalactic medium is thus not absence, but a different kind of presence. It's the baseline state, the condition against which other phenomena stand out. Without sound to fill it, the darkness becomes a perfect medium for light. Without acoustic noise, electromagnetic signals travel unimpeded. The silence allows other forms of communication to dominate, other ways for the universe to express its patterns. On Earth, we're so immersed in sound that its absence feels strange, even threatening. Anechoic chambers, rooms designed to absorb all sound, can be disorienting. People report hearing their own heartbeat, their blood flowing, the faint electrical activity of their nervous system. The silence becomes overwhelming because we're not adapted to it. But the cosmic silence is different. It's not the absence of sound where sound should be. It's the natural state of space, where sound has never existed. This natural silence has a quality of patience. The universe doesn't rush to fill it. Galaxies rotate over millions of years. Structures form over billions. The expansion of space happens so gradually that even light takes eons to notice it. Everything unfolds in this vast quiet, without urgency, without sound to mark its passing. Time itself seems different in that context. Stretched thin across cosmic scales, there's something meditative about contemplating the universe's silence. It invites stillness, encourages letting go of the need for constant stimulation. In the spaces between galaxies, nothing happens quickly. Nothing demands immediate attention. Everything simply continues, patient and unhurried. The silence isn't empty. It's full of time, full of space, full of the slow processes that shape reality on the largest scales. If sound did exist between galaxies, what would we hear? The answer depends on what frequencies we could detect. If we could hear gravitational waves directly, we'd hear a constant background hum from countless merging black holes and neutron stars throughout the universe. If we could hear the motion of gas, we'd detect low-frequency oscillations as matter flows along the cosmic web's filaments. If we could hear dark energy, perhaps we'd sense a subtle pressure, a gentle push expressed as sound. But we can't hear any of these things directly. Our senses aren't built for cosmic scales. We experience the universe through instruments that translate its phenomena into forms we can perceive. Light into images, gravitational waves into graphs, radio emissions into colors on screens. The universe's true nature is largely invisible and inaudible to us. We construct representations, models, visualizations, but the reality remains at one remove. Yet there's value in silence itself. It allows room for reflection, for thought, for the kind of deep attention that perceives subtlety. In the quiet, details emerge that noise would obscure. The faintest signals become detectable. Patterns hidden in complexity reveal themselves. The cosmic silence creates space for understanding, for patience, for the slow accumulation of knowledge that characterizes science at its best. When you close your eyes and listen to the silence around you, really listen, you might notice it's not complete. There are always sounds, breathing, heartbeat, distant traffic, the subtle hum of electronics. Perfect silence is rare on Earth, but imagine extending that silence outward, letting it grow until it encompasses everything, until no sound exists anywhere because there's nothing to carry it. That's the silence of intergalactic space, absolute and unchanging. And in that silence, the universe continues its work. Stars form and die, galaxies merge, dark matter shapes space, dark energy drives expansion. All love, it unfolds without sound, without announcement, just the quiet progression of physical law working itself out across billions of years. The silence isn't a flaw or a lack. It's the condition that allows everything else to exist, the medium in which the cosmic story unfolds. Perhaps silence is the universe's natural language, not a deficiency but a feature. It speaks through light, through gravity, through the patterns of matter and energy. These aren't sounds, but they're communications nonetheless, messages traveling across space and time. The universe doesn't need sound to express itself. It has other vocabularies, other ways of making patterns visible to those patient enough to look. So when we ask what sound exists between galaxies, the answer is none. But that absence reveals something profound. It shows that the universe doesn't need our familiar sensory modes to function. It operates according to its own logic, its own physics, indifferent to whether we can hear its processes. The silence is complete, perfect, unbroken by any acoustic wave. And in that completeness lies a kind of truth. That reality extends far beyond human perception. That most of existence unfolds in forms we can't sense directly, and that understanding requires going beyond immediate experience to abstract patterns and mathematical relationships. The sound of silence between galaxies is the sound of the universe being itself, unconcerned with observation, untroubled by awareness, simply existing in its vast, patient way. And perhaps there's comfort in that. The cosmos doesn't demand our attention. It continues whether we notice or not. Its silence is a gift, an invitation to stillness, a reminder that the most profound realities often lie beyond the reach of our senses, waiting in perfect quiet for those willing to listen with more than ears.